Jedna. Good morning. I hope that you slept well, and now we can start. I apologize for our video because it was only on vision, but without noise. Yes, I'm sorry. Ladies and gentlemen, dear friend, I warmly welcome you again after 4 years in Czech Republic. This time we are at the place of Horticultural Faculty of Mendel University Brno at the Lednice at south of Moravia. I would also like to mention that establish the traditional of silage symposium come to life in 1981 by Research Institute of Animal Nutrition in Pohořelice, but this research institute is now closed. Today we have 20th the anniversary. What began years ago as a meeting for the agriculture public has grown into an international forum where science meets, practices, and where experts in our field come together to shape the future of animal nutrition and food safety. I would like also to thank all of organizers who helped us to prepare this special silage meeting. Mainly Professor Doležal Petr and docent Eva Mrkvicová, Professor Skladanka from Mendel University in Brno, and to the workers of the Animal Production Research Institute of Animal Production in Nitra, who ensured the holding the symposium in Slovakia. But problem is that in Slovakia closed to organize this meeting, and in the future will be only on the Czech Republic. Long-time collaborators of Radko Loučka and docent Petr Homolka from Research Institute of Animal Production from Prague, Uhřiněvec, also engineer Menšík from Research Institute of Plant Production in Prague, Ruzyně, and Dr. Nedělník, director of Research Institute for Forage Crop in Troubsko, near of Brno. I would also like to mention all of sponsors. You can see on this screen all of sponsors, but also other places where poster and refresh are presented for you. Sponsors help us not only with financial support, but also with professional level of this meeting, which you will be able to evaluate, especially you as participants of the symposium. Over the next 3 days, we have an intensive program ahead of us. We will explore the latest knowledges in plant production, especially quality of plant in front of harvest, silage additives, microbiology of fermentation process, storage technology, nutritional chemical analysis versus NIR analysis. That is not analysis, that is only calculation. Next will be precision agriculture, especially using drones for agriculture. But beyond the formal presentation and poster session, I would like to ask you to the full advantage of discussion with participants of the symposium. The best ideas of often coming during coffee breaks, over dinner, or on the hallways between sessions. I ask you to contact with your college to establish cooperation. And most importantly, I thank all of you, the researchers, practitioners, and industry experts for traveling from near and far to be part of the community. With this, I would like to end my introduction and wish you not only a pleasant stay, but also new one information from lectures and posters. Lots of inspiration discussions. And now, please, Dr. Luis Nucio from the Brazil for an introduction first lecture. In International Stylish Science Society aims to strengthen the scientific utilization. This science society was established last year at Gainesville during a Stylish conference. I have to apologize Marketa Rinne from Finland, which is president of Stylish Science Society, but she is very busy and Nucio will replace her. Yes? Thank you very much, and please, for Professor Nucio, the first lecture.
Good morning, ladies and gentlemen. This is my great pleasure to be here today. I would like to speak my acknowledge, first of all, to my dear friend, Mr. Jambor, which kindly invited me to come from Brazil to come here today and deliver some of our most recent research. So I feel very thankful for this very kind invitation. This is a time to see and review and to meet some of very old friends I have been together before. And also it is a chance to, I was remember yesterday, this is my participation number 4 in Mr. Jambor's organization here. So I would like to have you all joining me in a round of applause on commemorating the number 20th organization by Mr. Jambor and his team. So please, a welcome to them. This International Symposium on Forage Conservation, in my personal opinion, this is part of the international agenda on silage science. So we are very lucky to be here today and to be participating on this. So thank you for the hospitality and all the organization for you and your team, okay? So it was a kind of a surprise for me also to come here today and represent the International Society of Silage Science. Marketa Rinne from Finland is our leader. She was supposed to come, but she couldn't by the end, so we apologize. She is not here, and I hope we will represent her properly and our group to introduce you the idea behind of this International Silage Society. So, sorry, is okay? Yeah, it's here. Thank you. So this is not a new idea. This is coming from, I would say, the last 6 to 8 years to try to have an international society exclusively for silage. This is not only because of the idea of getting together more and more people, but we are recently struggling more to have our publications coming to the common journals. So actually the journals, they understand our silage trials not as they were taking them in the past. So we are all the international community on silage science, we're pretty much struggling on having our publications coming into the very last end in the very high quality citations. So the idea behind of the society is to make this stronger, and maybe in the future to have the chance of have our own journal. So the first time when this was properly presented to the scientific community, it was in 2023 in Beijing. At the time, I was running a program at the China Agricultural University, so I was there with the leaders from the organization from the International Silage Conference down there, Professor Fu Yang, Professor Xu Shenggu, and Professor Yiming Chai, which is here today. And all the Chinese, they have done a wonderful job organizing this just after the COVID restrictions. So the need for this international silage society was acknowledged at the time. The aims were discussed, and a positive feedback from the conference and attendees was received. So in 2025, 2 years later, we were attending the meeting in Florida, where Professor Bola was the chairman at the time, and then formally we have held this official launching of this International Silage Society. So the idea behind the International Silage Society was a mission to promote the advance of silage science and technology through research, education, industry, and enhancing the fermented feeds for animal production and efficient biomass preservation for bioenergy, biorefineries, environmentally friendly recycling of agricultural and food industry byproducts. So almost all the chances to grab together all the players from the silage, they were part of this interest. This is a non-profit proposal. This organization is voluntary and organized by the scientists and the society industrial related with the silage science and technology. And the major aims related with this is the establishing the international platform and networking to prompt a worldwide exchange in the communications of the silage research, extension, and education. I have to make a small break here just to let you know that all of us which are working at university level, we are recently facing a kind of a new challenge in how educate the new generation for silage. This is not very easy. And the idea behind of this is we are trying to prepare people to be very, very specialized. However, silage turned out to be a typical, very complex problem. So maybe we have to review our guidelines of education in order to better prepare people for the future, in order to prepare them for complexity, which is typical from silage. Silage is not very easy. Silage is something that needs to understand about many different things, and this was the beginning about 100 years ago when people used to be prepared to solve large problems. So silage needs to have some education for complexity. So in order to improve the impact of this silage society, the research and technology worldwide, and extend the silage science and technology to regions of the world where this is not well developed yet. For instance, I will give you, in my very last slide, the idea that we voted and approved that our next International Silage Conference will be held in Nigeria, in Africa, in order to give the extension of the benefit of this knowledge to many of the countries which are very important stakeholders and players in Africa. So today we have here Douglas representing the South Africa, and my friend Douglas, we will see him and a lot of fellows from Africa in 2028 in Nigeria. So how do we become a member from this idea? So far, we are still working on the organization, and I try to highlight here, this is still very personal. So please, for those of you which are willing to participate, send a message to Marqueta. Marqueta is trying to grab the first mailing list for all the people which is willing to participate on this. So maybe this is the most important slide of my presentation. Marqueta wants me to come back home with more than 100 new members. Please help me on this. Otherwise, I will be a kind of shame of representing her properly here. If you don't mind, just double check, send the email 2 times, please. This will help me even better to make sure everybody is getting into the list. So we want to have all the academics, all the students, the industry representatives, everybody which is playing silage all over the world is very welcome to this, and also the companies and the company teams. Nowadays, in my personal opinion, the thing that we need the most is to have the technical people from companies participate on the scientific meetings. This meeting here represents a very important message to that. It doesn't matter if we have all the university together. If we don't have the companies and the technical from companies together, our discussions will not go further enough. So we need more and more the companies participating with their team to the discussion, not only to contribute, but also to listen the ideas coming from the university and the research institutions. So this International Silage Science Committee is primarily based on the board, so-called board of the Continuum Committee of the International Silage Conference. And nowadays, this board is represented, our older fellow is Rick Muck, which is representing the old times and the very good names, important names that we have in the silage science, the founding of the silage science. Rick Muck is now retired, but he is still active on the board. He participates in all the discussions, and he was the chairman of the International Silage Conference in Wisconsin in 2009. After him, Marqueta was representing the board, and now she is the leader of the board because she was the chairman in Finland in 2012. I was the next one in 2015 in Brazil, and I remember that some of you were in Brazil with me more than 10 years ago, and thank you for that. I hope we will see in Brazil soon again. Professor Sudekun from Germany, he was the next one in 2018. And then we have the restriction from COVID, and we only held this conference in 2023 in Beijing. We postponed for 2 times. We were supposed to do this in 21, but then we moved it to 22, and only in 23 we could have this, finally, this meeting after the COVID. So Fuyu Yang and Xu Shengwu, they were the co-leaders there. And the last one was Professor Bola in Florida in 2025. So this is the board of this so-called International Silage Science Society. And this society will have also a regional members participating and representing the needs from the 5 continents. So we will have nominations for members from Europe, from Asia, and Australia, Africa, North America, and South America. Our next steps from today and further, they will be establishing the regular meetings. We are already doing that, of this executive board, file the registration of a society and a bank account. We already done this. We start with new letters to the members. Marqueta is working in our first one to facilitate the organization and continuation of International Silage Conference and support the next host in organizing the 21 International Silage Conference. Maybe you are not aware of this, but this is not an easy task. Every time when we are planning for the next one, we are still struggling to capture some funding and sponsoring. This is not very easy thing to be done. The idea behind this is to make the society meetings easier than we are facing right now. So we are still trying to convince the companies the world is not easy. The geopolitics is making the world even harder to founding this type of initiative. So the establishment of a permanent website and access to the previously published proceedings of the conference. So we need to have a place to make a host for all these proceedings from previous meetings. And finally, to evaluate the possibilities to publish in our own scientific journal. We are now discussing this almost every other month. So, one of the main issues behind of this is the continuation of this. When I mean continuation, is not only the matter of making the continuation of this conference, but the willing attitude in order to have more people educated in the silage science, getting to know what we have done in the past and looking towards the future. So this is not very easy yet. We will have a future meetings and announce in a proper time, and please consider this as an interest to you and your networks. So the ISS board will take the decision of the next host, and we will also provide a guidance for organizing committee of the conference as needed. So the idea behind of this is we will try to have a kind of a worldwide collection of suggestions in order to decide the next meeting of the International Silage Conference. Pretty much we have done this by deciding for Nigeria recently. And I'm coming to the end of this presentation. So this is just to remember you all the meetings that we have done so far. Since the first one that was represented in 1970 in Edinburgh, in Scotland. So this was the number one. This was a really impressive how many of those were being done all over the world. And the first 25 years, probably they were also being hosted in UK. And later on, we start moving across other countries. And now the next one will be, as I mentioned before, in Nigeria. So I hope by our next meeting in Nigeria, I will have the chance to see you all there participating on that and try to bring with you at least one additional partner. If we have you and someone else, we will have a beautiful meeting in Nigeria. So with this, Mr. Chairman, I'm open to the questions and to have all your suggestions, and thank you very much for your very kind attention. Thank you.
Thank you very much, Luis. It was an excellent speech, yes, about the future of the silage science. And it is very important. And a lot of you visited the Gainville last year. And you know the start, Marketa Rine, yes, but she cannot visit us, yes, and I am glad that you are here, and we are listening about the future. And that is important because the silage fermentation is a special process, and we have combined silage fermentation and fermentation in rumen. It's very important for milk production, yes, and that I think that will be very good some lecture in our meeting, which will be take about it. Please, do you have some question for the Luis? Nobody? I hope that during the discussion in outside, thank you very much for your first lecture. Yes?
Okay, thank you.
And now I would like to invite second lecturer. I would invite Professor Hackel from Prague, Agriculture University from Prague, and his lecture about forages quality. Please.
So, good morning, ladies and gentlemen. First of all, I would like to thank the organizers for the opportunity to introduce our topic from the field of forage production. It's a highly important agronomic step which precedes the forage conservation, as only high-quality forage can produce high-quality silage. Yeah. So it's extremely important to understand also the management of forage crops in the field to produce high-quality forage. Our topic today is focused on mixtures, forage mixtures. It's important to say that it's not a new concept. It's a very well-known system. It has been used at least for 200 years. However, there are still so many innovations and research which is important in optimization of this kind of forage production. So forage mixtures are the topic for this presentation. Here we can separate these two groups of forage stands, as forage can be produced in different way. First of this is a nature and semi-nature grasslands. So it's a permanent system which is naturally rich in species composition. There are plenty of them, and there is a variable production and quality of the biomass. However, these systems sometimes is more focused on ecosystem services of the production of the system, not only forage production and forage quality. It's an important part of landscape, and we need this, and there is intensive research in optimization of this kind of management. And there can be also high variability in composition. As you can see, it's the same meadow. There is 1 meter between these plots, and this is intensively fertilized with nutrients, and this is without fertilization. So you can get very rich stands, and but the focus here is mostly in the environment and ecosystem services. So our interest today is move to the sown grassland. So it's the system of the production in the field where we sown the mixtures or monocultures for forage production. Maybe you know the term lace. It means temporary grasslands in the field system. Here, I'm sure you know that especially Western Europe tends to produce forage biomass in ryegrass monoculture. in comparison to our region, where we have tendency to produce, to use the legume monocultures, lucerne or red clover. However, all these systems are based on the monoculture, which is easy to manage, is highly productive. You can easily determine the quality, it's fine. However, the trend also in the field, there is a trend to promote the mixtures for the production and looking for the special combination of the species which can bring something more for the production and also for environment. So it's a slight introduction to this definition, and our question here that we are looking for sustainable productive system which is productive but maintain also some ecosystem services or high diversity and so on. Which species can be used in these mixtures? Traditionally, they are legume grass mixture. There are plenty of species of grasses and legumes which can be combined, and there is decades of research how we can combine this. However, what is slightly more new, it's the herbal ley. Maybe you know the definition. It's sometimes used, and it means that it's a mixture which includes also the non-leguminous dicotyledonous species. In principle, legumes are also herbs, yeah, but if in the precise botanical definition, but if you can meet the definition herbal leys, it means that there is the grasses, legumes, and other herbs. The main, I think mainly widespread species is plantain and chicory, which are intensively used. It started in New Zealand, but now it's also popular in Europe. And as is demonstrated here in the pictures, I think you know this species very well. But there are also other species. But this presentation is mainly about this, as there is plenty of research in this. So we need also research how to introduce these species to the traditional mixtures, and especially focusing on the functional diversity, where there is a species complementarity, they cooperate together, so the behavior of species in the monoculture is not the same as the behavior of the same species in the mixture. So we need this kind of research which can help us to understand these interactions in the mixtures. What we can use for this, there are traditional questions which we have, how many species we need in the mixture, and below this you can always see the method which is used for the evaluation. So there are traditional regressions if you compare something, biomass production, with the species richness, and you can see, yeah, it's better, higher, we need more or less species. If you can compare the community's performance, there is an analysis of variance, which is traditional way how we can compare it. However, the modern, or I said, is this system of the diversity interaction modeling, which can help us to understand how the species interact in the mixture and which proportion or which species combination is the best for the particular trait. It can be yield, forage quality, crude protein content, but also anything else, what you can imagine. So it's a background for this, and this diversity interaction modeling is a new approach which we can use in the mixture evaluation. Now let me shortly introduce the LegacyNet network. It's a voluntary international network of experiments covering 26 sites across 15 countries in all over the world. And there was idea to have one common field experiment across all environments, and this experiment consists from 6, this sword in the experiment consists from 6 forage species, always 2 grasses, 2 legumes, and 2 herbs. There are examples which can be used, the species you can see, but the species was not uniform across the world. There are different species in different regions, but the system was the same. You always have 2 legumes, 2 grasses, 2 herbs in different combinations, but species were different. However, it's necessary to say that chicory and plantain was always used, as there are not so high diversity in the herbs composition across the world. And there were 47 plots of this combination under standard nitrogen fertilization, and also 5 plots where was the standard for Western Europe, so it's a grass monoculture under intensive nitrogen fertilization. You can see the average of the nitrogen rates, but it's average across the world. Yeah, so it's not always was the same rates. And here is a ternary diagram, which is usually used for the presentation of the result of this kind of the research, where you can compare the effect of the combination of the species. So you can, maybe you are not so familiar with this, so in each triangle corner, you can see the grasses, legumes. Legumes here is mainly white clover and red clover. Grasses was a timothy and perennial ryegrass, and herbs was a chicory and plantain. And on the edge of the triangle, there is always binary mixture. So it's mean the grasses, legumes. So it's here in the middle, there is 50% grasses, 50% legumes. And here, so binary mixtures on the border, and inside you can imagine the different combination of the species. The idea is that there is not one solution, there is not one optimal combination. There is an area, the space, where more combination can bring the highest yield, the highest quality, what you can evaluate. And so now the first result, which was published in the Science last year. It was released last year, but it was published this year, of the whole team covering the 26 countries in the LegacyNet network. And here in this this feature, so what was found on average across sites, that there is a multi-species mixture with 6 species, and there was increase in the yield 11% if you compare the productivity of this mixture with the one grass with high nitrogen fertilization. And if we consider traditional 2 species legume grass mixture, there was even 18% increase in the yield. So in spite of mostly double nitrogen fertilization, the forage productivity was higher in the mixtures than in comparison with the grass monoculture under intensive fertilization. So it's a first picture, very important, that showing that high productivity of mixtures. And here on the right side, you can see the ternary diagram showing the maximum yield area. There is a green color showing the level of the yield. And so low 8 tons to 13 tons, it's an annual dry matter yield. And the 11 tons is a perennial ryegrass here. And here's the blue color is the center of the highest productivity with the combination grasses, 24%, legumes, 60%, and roughly these values. And here in the middle, there is the multi-species mixture with six species combined, each species in the equal proportion. So, as I said before, there is no one solution. You can see that if you have this combination in this area, you could cover the maximum effect of of the mixture. What is also interesting that, especially under climate adaptation, here you can see very large gradient in the temperature. So the Canada side with 2-3 Celsius degrees as an annual temperature compared to the New Zealand here it's almost 13, 14 Celsius degree. Here is the Czech Republic, as one side was coming from our research station. And here you can see that there is the potential of the mixtures was derived by the temperature as a difference between the intensively fertilized grass monoculture and the mixtures was increasing with the temperature. So under higher temperature, you can get more from the multi-species mixture in comparison with grass monoculture. So there is a clear potential that mixtures are better adapted to the higher temperature, to the changes in the environment, if we are still talking about forage productivity. And now, to quality, if we are talking about quality, there is a very well-known yield-quality trade-off. So it's nice that our mixtures have higher yields. However, there is also some response in quality because usually higher yield results in the lower quality. There is some theoretical explanation, but I think you know that main driver of this is changing of the leaf-stem proportion. When with increasing yield, you have decreasing leaf proportion, and the leaf as a metabolic part of plants has higher quality than structural tissues, stems. So it's clear that forage yield is increasing, but the leaf yield is probably the same, and stem yield is higher. So we cannot maintain the quality with increasing yield. It's a physiological. It is for the Lucerne monoculture, eh? And there is also similar trend for the nitrogen, as these changes, leaf stem proportion, are responsible for the nitrogen dilution in the crops. So we cannot keep high nitrogen with increasing yield because there is a natural changes in the leaf stem proportion, which results in the decrease in the nitrogen. And even if you use intensive fertilization of grasses, you can never keep high nitrogen content. There is still the dilution. So it's clear that with higher yield, you can have lower nitrogen content. And there is also time effect with the stem maturation. So if you wait longer and longer, there is a lignification of the tissues and the quality decrease. So it's clear. But what we can expect from our mixtures is the same. Is the yield increase is following by the quality decrease? Fortunately not. Here is a metabolized energy yield, and so you can see that it follows the yield. So highest yield of biomass results in highest energy yield. But here is a nitrogen. There is a metabolized energy content, and here you can see that there was minor changes. There was the green, and so there is only 0.5 megajoules. And if you consider the green and the yellow color, there is only 0.2 megajoules, and it covering the most part of the features. So what can be shown here, that the herbs really don't contribute to high energy content, but mixtures of grasses, legumes, and herbs cover the sufficient area very well. So here, the decrease in the increase in the yield was not connected, was not associated with the decrease in the nitrogen metabolized energy content. What was also interesting that the yield, there was the multi-species mixtures with 6 species, there was yield lower than 9% in comparison with the highest productive system. However, there was also a reduction in the variation of the yield. It is also very, not very popular, but it is the trait which has still more and more importance, and is the yield stability. So it's not only a question if I reach the high yield in one moment, I need a stable yield across from year to year, from cut to cut. So here you can see that the 6 species mixture can be able to reduce slight variability of the yield fluctuation. So it's also important mainly in association with the climate change adaptation. Regarding to crude protein yield and concentration, there you can see the similar feature to metabolize energy. So there is legumes clearly produce the highest crude protein yield, but it was true also for the crude protein concentration, where you can see that legumes has the highest, and grasses and herbs has the similarly low crude protein content. But it's not surprising, and it's a clear pattern where legumes are very rich in nitrogen. But there is other question, if we really need high crude protein content, as it's also well known that forage legumes contain excess of human degradable protein, usually about 80–90%, and most of the nitrogen is released rapidly in the rumen, and due to the lack of available energy, it leads to the nitrogen losses. So maybe the situation where we have the lower crude protein yield in the mixture may not to be detrimental, as we don't need extremely high crude proteins as it is in legumes. So maybe it can help with the improvement of nitrogen use efficiency, as there are 2 strategies which is presented here, the lower crude protein content in the ruminal diet, which can improve this efficiency, which is supported by range of studies. However, there is other point, and it's a better balance between crude protein and energy in the forages. However, this evaluation should not cover only traditional water-soluble carbohydrates versus crude protein, as it's extremely favored grasses, as has higher sugars, water-soluble sugars. However, we should consider also other fractions of the carbohydrates which are able to improve this nitrogen use efficiency, as is also pectins and starch, and legumes are more rich in pectins and starch. So there are also studies which propose the non-structural non-fiber carbohydrates compared to the not all crude protein, but especially the non-protein nitrogen and the B1 fraction in the crude protein fractionation. So it's other point of view how we can look on the mixtures in this point as a nitrogen use efficiency. And indeed, there is a potential that mixtures, if you combine different species with different crude protein fraction and different sugars fraction, it can help me with this. However, the question stays if it is effective, measured by animals, and if it is stable across season. And it's not fully stable, as you can see that there are seasonal changes, at least between grass, herbs, and clover and legumes. And there can be also differences with different species within each functional group. So it's not really so much stable. And the stability across years is presented here in this feature. It is also in the paper, in the proceeding. So it's, we can get different energy protein proportion in the mixture. However, across year you can see that there is a double value in the Sain-Foin Lucerne mixture in comparison with the pure Lucerne. However, you can see that over years, 3-cut management and 3 years, you finish with the same value. So, sure, the potential is here, but the question is how we can manage the mixtures in the field to maintain the value across season and years. Other point is mineral content. It's also very well known that the mixtures, that herbs and legumes contain more minerals, so there is a better macro and micronutrients content in this multi-species wort. And even, what is also interesting, sometimes we can get higher animal performance in spite of the general nutrition quality was not changed. Yeah, so mixtures, if you compare energy, protein, and the basic quality parameters, it is the same, but the final animal performance is higher. So it's another benefit of mixture, which should not be closely related to the improvement of forage nutritive value. And the last part of the presentation are so-called bioactive compounds. I'm sure you have heard about it, and the forbs and legumes present plants which are naturally rich in the secondary metabolites, and it can help to modulate rumen fermentation, mineral fermentation. You can see everything here. There is a table covering the species and the bioactive compounds, concentrations, threshold, and so on, and the mode of actions, and what can C do it. So, and what is also, what I also would like to present here is that there is not only effect on the yield and quality, as was a traditional research question in the past. However, today there is also environmental impact. So how many methane, how many greenhouse gases, how many we can pollute the environment by anything. So it's extremely important to consider also this environmental part, and here the bioactive compounds can help us. In the last part of the presentation, I focused especially on the nitrogen use efficiency, as we already discussed in connection with the protein energy ratio. But because there are also species which can provide some bioactive compounds which can improve the nitrogen use efficiency, and it's especially associated with the contents tannins and the polyphenol oxidase. There is an explanation that there is a protein is bind in the rumen, and there is a protection and reduction protein during the rumen degradation. There are very nice studies of Koblenz and Graeber which calculate that each condensed tannin unit protects 0.6 unit of the crude protein. So if we need to reduce rumen protein degradability from 80 to 70, and if we have 20% of crude protein for legumes, we need about 3.5% of tannins. So it is not absolute value what we need, but it depends on the crude protein content and in the forage. So but it is one side. The second side is how it is work in reality. Yeah. And here is a high diversity in the tannin structure. So it's not tannin-like tannin. Some tannins from Sain-Foin are not so effective in the reduction of the rumen degradability like different tannins. And we also have high variability and often marginal concentration of these compounds. And the other trouble is that current analytical methods are poorly suited for the field monitoring. It's not so easy to measure these compounds, and we need it in the field, but it's a problem. There is a clear systematic reduction in the protein degradation, it's right. And there are mainly changes in the partitionation of the nitrogen extraction. However, the effect of nitrogen rotation by animals is not always evident. Yeah, so it is a potential, but if we would like to measure it on the animals in the final stage, it's not sometimes working. I can say it's usually it's not working. And even if we have the low protein diet, it can be, this condensed tannin are even detrimental here. And the polyphenol oxidase in the red clover, for example, is only active in the silage content, but not for the different way of the conservation. So, summary to this, despite of biomass overyielding, there is not reduction in the forage energy content, and there is an increase in the total metabolized energy yield. So mixtures are more productive, and this is not associated with the reduction of the quality. It's fine. Mixtures improve macro and micronutrient supply. It's also clearly proved. And there is a potential to improve the nitrogen use efficiency. However, it's not always working due to some reason which I have mentioned before. Bioactive compounds can help also with different topics. It's clear. But main constraints here are unstable species proportion and concentration of target compounds in the field. And what we need understand the interaction between species in the mixtures. So we need some modern way high diversity interaction modeling, which can help us to understand what's happened, why the mixtures has the different performance. We need reliable tools to assess the in situ concentration of nutrients, and also some breeding programs which can help us to improve the minor species which are not usually so productive, and maybe the bioactive compounds concentration is variable, and to stabilize the concentration and some quality of these compounds. And also we need adapting some suitable agronomic practices to the multi-species mixture, so which management is needed to stabilize the proportion of the species. It's nice that some species has high content, but if it has low proportion in the mixture, it's a problem and we don't get the final effect. And it can be summarized that transdisciplinary research is needed, so it's nice, like it was presented before for silage. We don't need only forage specialists for production, we need connection between forage, crop science, animal science, ecology science, and make it together to better understand and better utilize the potential of the multi-species mixture, which can help us with the coming challenges like the climate change. So thank you for your attention.
Thank you for your lecture. It was very nice about the huge ideas of new effect for the quality. But I have a quite easy question for you. What do you mean for comparing of the monoculture forages and mixture forages for the cows? What is better?
It's not easy question. I think for cows or for ruminants, I think the base is the stability. So they need the stable feeding ratio. So if you have high diversity species, it's more complicated to have the stable proportion, stable quality. So maybe from this point of view, the mixtures are more complicated, but mixtures are more complicated in everything. It's not only productivity, it's a quality, it's the change. But they bring, indeed, they bring the opportunity to improve the environmental impact, which is also criticized by many of people that if we really don't, if we really need ruminants at all, if we really need the forage production, if we really need the whole system, but without animals, without permanent grassland, without this mixture, I think the whole system is less stable. But maybe mixtures bring some complication, but they provide clear benefits for us.
And the next question, it's about microbial protein. Yes, if you study, compare the quality of the forages on the production of the milk microbial protein, because microbial protein is very important for the economy of the milk production.
I am not aware about any research in this kind of the field in relation to the mixtures or even multi-species mixtures.
Yes.
If there is some research in relation of mixtures and microorganisms, it's usually in the soil microorganisms and the diversity of the soil or soil life, but not here.
Thank you. And next question for David Seal, please.
Are there any studies on the effect of mixtures on the composition and the quality of the milk, milk protein, milk fat, even the maybe the taste of the milk?
I know studies about effect of the diet of the ruminants on this, but I don't know about any special multi-species mixture on this. Yeah, so yeah, I don't know, but we need this kind of the research, sure.
Thank you. Next one, please. Nobody? Thank you, Professor Hackel, for your presentation. And now next step is I would like to invite to Silvia Ross from Hungary for the special lecture about NIRS, because NIR is not analyzer, it's only mathematic results.
At first, I would like to say thank you, Chairman, for the invitation. I'm always happy to be here, and thank you for being here, for the audience. So, my presentation will be more technical than scientific, because there is a new life in the NIR era, in the NIR world, and I would like to introduce the global networks to show the details, the advantages and disadvantages of this new system. The time is limited, that's why I can't tell the details, but you can find in the paper a lot of information about the technical background of the NIR diodes and optical technical background, and the general information in the paper. And we summarized the information about global networks, and we compare the near spectroscopy and conventional wet chemical analysis. And you can find the basic information about the global networks, NIR networks in the world, and the comparison of the global networks versus local calibration strategies. And you can find at the end of the paper a lot of information about the portable NIR systems, the future. So this is an evolution in our life, in the forage science. We started traditional lab analysis many decades ago. But now there are NIR systems all around the world, and the portable NIR, the next steps. And the last step, what we see now from the future, the real-time inline NIR systems, which give continuous support for precision feeding and forage management. So it means that we are on a special pathway to continuous decision making. So the NIR system now is a tool in the hand of farm managers, nutritionists, veterinarians. So what are the key drivers for this development? Of course, we know that the forage quality is determining from feed efficiency or animal performance of you. It's okay, we know it. But nowadays, in the dairy industry, we need rapid decision making and we need information quickly. So we don't have time to wait 1 week or 2 weeks for laboratory results. It's very important that the Cornell University introduced the dynamic rumen model. And this model based on digestibility data. So the modern nutritionists need not just nutrient content and fermentation parameters, but even digestibility data in the report. And the wet chemical laboratories can't give this kind of data. It's very important. So we need multiply parameters because the end of the forage is the rumen and the milk production and the diet. And if you would like to make a good diet, we need a lot of information together in the same time. Not just the nutritional value, but fermentation parameters, and we need software input data derived by the new softwares like AMTS or NDS. So the softwares and companies who develop these softwares drive this kind of development of NIR laboratories. And in the future, we will need in-time data. It means that we will be able to react quickly within some minutes if something wrong, if we see that there is animal health problem or there is lower milk production or lower milk fat, we can make a very quick reaction if we have real-time monitoring system and in that case it is a real precision feeding. So the dry nears, it is the general at the moment. We take the sample, we dry it, we grind it. After we make the scanning, so we will have a near spectra, and with chemometric models, the statistical softwares find in the reference database the nutrient content, and final result is the predicted data and parameters list for the forage. What are the critical points? Because we feel that we have many doubts if you look at the NIR, even now, even still now. The critical point is the analytical accuracy and precision. The calibration quality determines accuracy, and we need a continuous development on it. And the size of database is a critical point because if we have a smaller database, it will reduce the reliability of the data. These are very important points. So, when we compare results of the same sample derived from an NIR lab or a wet chemical lab, generally we have questions and we can see differences. There are many reasons, there can be many reasons of the differences. So we shouldn't decide that, oh, NIR results are not good, because if we don't consider the background. The first is the sample heterogeneity. Accuracy will be different if we look at if we measure a corn silage or a TMR, because the TMR is a complex matrix with higher heterogeneity. Or if we look at the reference methods, it's a very crucial point. It's a rather crucial point. Why? Because we always compare our NIR results to a standard wet chemical lab parameter list. But generally, the routine users don't check whether the methods of the wet lab and the methods applied as the reference in the NIR is the same, or whether there are differences. If there are differences, in that case, the difference between the results based on the wet chemical lab differences. And it's not the NIR, it's not an NIR problem, it is a problem of the wet chemical lab methods. And we should consider that if the database is limited, and the peripheral area or reliability will be lower. So very poor or very good silage data can be on the peripheral area on the database, and it can cause higher bias, higher deviation. And of course, the statistical model is also important, because it's possible that we have a big database and we use similar methods, wet chemical methods for the reference database, but the statistical method, what we use, is not adequate. So there can be many reasons. It is an indirect predicting method. It means that when we have the spectra, we have to find similar spectra in the library, in the spectral library, and after the softwares find with chemometric model and system the appropriate nutrient and digestibility data in the reference database. That's why it is indirect. I would like to show you what can happen if the reference methods are different. And I would like to show you that sometimes the NIR technology may have higher accuracy compared to old wet laboratories. The problem that in the case of global networks, global NIR networks, generally has a central lab and is a huge lab with a lot of chemists and a huge facility to develop the different methods. They are very quick and very good in development. And sometimes these global networks use state-of-the-art methods, better and more developed methods than some traditional wet labs. But we use the wet lab data as standard data, and it can be a problem. So one critical point for us as a leader of an NIR laboratory, that the wet chemical and in vitro reference methods are not standardized worldwide. And there are continuous developments of the different lab procedures. So it means that it reduces the comparability, and it can cause discrepancy. Look at just some samples. Crude protein. You can tell me, oh, it's clear. No, it's not clear. There's 3 different types of Kjeldal protein, crude protein data, according to the German, the Danish, and the Dutch system. Okay? And there is the DUMA. Okay, the DUMA can be comparable with the crude protein, but even the crude protein methodology, we have differences. Or look at the fiber analysis. 25 years ago, 30 years ago, NDF was general. But nowadays, we have eNDF, amylase treated NDF. We have NDF-OM, ASH-corrected NDF, and we have eNDF-OM. So the farm managers, the veterinarians, and decision makers has to check whether it is eNDF-OM or NDF-OM or eNDF. They can't do it. And it is a problem because the results can be different. Look at the digestibility. In the United States, they use NDF degradability for first 30 hours. It is general. But American academic association decided the NDF-D48 is the best. In Europe, we used it. We are happy that American academic confirmed that 48 NDF-D value, but it can cause a misunderstanding if you look at the data. Starch. It's awful. Why? Because in Europe, in Central Europe, the polarimetric assay is general. But in the global NIR network world, we use enzymatic photometric method. And in the case of TMR, the difference is minimum 4% in dry matter. So the starch methodology is different in different laboratories. And if we compare a modern NIR data to an old type wet laboratory data, it can be confusing because the reason of the difference is not the problem of the NIR. At the background, the problem is the different method. And sugar is the worst because we have ether extract, Lufschol methodology, and we have water-soluble carbohydrates, and these are different. The global networks gave nowadays both. But if we have just one, we are not able to compare. For example, VST is not comparable with ESC. So it is another sample that we would need harmonization because this kind of variability reduce comparability of the wet results, wet lab results, and NIR results. Okay, so a worldwide harmonization of the reference methods would significantly enhance comparability, transparency, and reliability of the NIR results. Oh, look at this sample. I got then a coincided sample from Dr. Jambor, and I compared different laboratories, a wet laboratory, wet chemistry laboratory, and 3 NIR laboratories. Look at the starch. We confirmed that there is significant difference in results. And in the case of NIR2 laboratory, the reliability and accuracy was low. If you look at the ADF, we haven't found a significant difference, but we have seen that the NIR1 lab had very low RPD value. This is residual predictive value. It means that there is a big bias, so it's not reliable because accuracy is not stable. Okay, what is the conclusion? What can be the conclusion? If we look at the data, we compared the NIR data to the wet chemical laboratories, but we did not check the methods what the wet lab used, and we did not compare with the reference methods behind the NIR. Who can do it? Farmers can't do. Farm managers can't do. But it's not easy even for us, for scientists, to compare the laboratory methods. And generally, a comparison of the reference method and versus wet chemistry lab procedure is a lack. So when we decide whether the NIR data are wrong or not reliable, please consider there can be many factors behind, and the method differences and the lack of harmonization can be one reason of the differences. Okay. Of course, the big laboratories, the global networks, have special own data for reliability, and these are available. So it's not secret. I collected the most important global NIR laboratories data. And in our world, there are new parameters for statistical analysis. So it means that there are special statistical methods to compare the different laboratories' accuracy and precision. Okay, and now I would like to compare the dry near spectroscopy, the global dry near spectroscopy, and conventional chemical analysis. Because generally it is the main question, which is better, what we should use. Okay, there are advantages and disadvantages. We know that the near technology is very rapid. We don't use chemicals. It's a huge advantage. We can apply on a farm, real time or with plug and play technology. There is a huge capacity of the central labs for development. And there are many data. For example, digestibilities, starch digestibility, NDF digestibility, key D values, what are not available in wet chemical laboratories and need for the software. What are these disadvantages? That is a dependent status when somebody is part of a global network, of course, and accuracy and reliability is always a question. After 30, 40 years, we have to prove that these data can work in the dairy industry, but I see the doubts always. There is lower sensitivity for local differences, and that international standardization is needed. Okay, a conventional chemical analysis have special advantages because accuracy is perfect, and all over there are universal methods. There are differences, but the wet results are much more comparable to each other than wet and NIR results. But there are many limitations of the wet chemistry. It's time consuming, very intensive procedures, use hazardous chemicals, it's more expensive, and there are missing data. The CNC PS data are not available, digestibility data are not available in the wet chemistry. So the near spectroscopy able to give a rapid result, cost-effective result, and is able to support real-time decision-making. While the conventional chemical analysis provide maximum accuracy. Integrated approach would be the best. I recommend to use the NIR as indicative results, and if we need a deeper view, if we have a trial or if we have a serious health problem, in that case we can make checking in wet chemical laboratories. It is a combination of the two systems. Look at, it is a comparison of near spectroscopy and the chemical analysis according to the speed, sample preparation, chemical use, accuracy. It's very important, accuracy. If a global network has a huge database, a robust database, it may have high accuracy. But accuracy depends on the database size and the chemometric model used. Of course, in near spectroscopy, we can't measure minerals. Why in conventional chemical analysis, it's an excellent opportunity. The cost is very low in the case of near spectroscopy. It's much higher in conventional technology. We can use the near spectroscopy on a farm, and we have many plus data what we need in formulation. And these global networks are more flexible because the background is the central lab generally has a lot of chemists and a huge good facility laboratory facility, so they can be very quick to react in the market demand, and I think they are more competitive. The competitiveness is much better than the conventional chemical analysis. Okay, the global NIR laboratory. I was talking about it, but I did not describe what is global NIR network. I have chosen 5 different systems. European systems, there's Eurofins Agro, Dairy1, Dairyland, Rock River, and CVS. This is the Cumberland Valley. What is the character, what kind of characteristics we can describe this system? There is always a central laboratory with good facilities, opportunity for developments, with a lot of with huge staffs, and they make large. They have already generally large database and robust calibrations because they are working all around the world. They have international standardization because they need to standardize the methods within the system, within the global network. And they have local satellite laboratories. These laboratories are small labs. They collect the samples, they grind, and they make the scan. And they use a standard procedure fixed by the central laboratory. It's very important to mention that this kind of network, global network, is opportunity for that kind of countries who hasn't got local calibration capacity, or it is just limited. Just like some countries in Asia or in Africa, it's important they wouldn't be able to make their own calibration, or it would need 20 years. But if they join to your global networks, they can start the service within half year. And in the background, there is a huge and robust database, sometimes 40 or 30 years old database. And what is the biggest disadvantage is the dependency. That the calibration database, it is in the center, and development facilities are in the center, not the satellite labs. Nowadays, I read a very important conclusion in a paper. Hussein and his team had a message that the multi-regional calibration datasets significantly increased prediction accuracy. So the NIR, if this system is a global system with the robust database, has huge advantages, and this kind of system can improve significantly the reliability of the data. So there is a big difference with global networks and local calibrations because of the dataset size, the differences of the dataset size. So if we compare the global networks and the local near databases, we can find many differences. So the advantages of the global network, that the global network has generally high data set, big data set, sorry. It's robust and it increased accuracy, okay? There is a standardization activity, and that's why they can overlap the world. In many countries in the world, they have opportunity for continuous improvement. It's important. They can harmonize the different measurements and procedure within the global team. They can be very fast in response to the market demands. And their competitiveness is really good compared to the local near data sets. If we look at the advantages of the local near data sets, they tailor to the local feed resources. Okay, and adapt it to the regional environmental circumstances. They have representative data for the local silages, local crops, and they have autonomy because the calibration data set is their own property. So they have an autonomous system. They are independent from the cloud system and international systems. They have greater transparency, and they can make a rapid adaptation. So the global databases maximize robustness and standardization, while the local database maximize adaptability, flexibility, and autonomy. Okay, but there are disadvantages also. If we're part of a global network, we haven't got sovereignty, calibration sovereignty, so the local laboratories can't develop calibrations. This is a dependent status. The vendor lock-in risk is also a risk, a chance. The local variability is a question. There is limited adaptation because it's a worldwide system. There is limited transparency. The data privacy and intellectual rights are also a concern. And of course, the dependency is a huge disadvantage in this situation. Advantage and disadvantage. If we look at the local systems, the local database need a lot of effort in a generally small lab, a lot of investment. They develop continuously the local data set, and it's very expensive. They have limited number of samples, what is the biggest disadvantage. They are slower than the global network, and they have lower competitiveness because of the lower staff, lower infrastructure background. So neither approach is universally superior. Both involve trade-off between standardization or flexibility. I can't tell which is better. There are advantages and disadvantages. The hybrid system would be a solution. What does it mean? That in the global network, if we apply local refinement, it's a combination of advantages. It means that in a global data set, we can apply local data also. For example, the Eurofins Agro made calibration for the South African Republic for Kikuyu grass. It is a local calibration, but it's part of the global system. So it would be the future, and it would be an effective way of combination, effective combination of the two systems. So now I would like to give more information about the global networks, facilities, and service. In our laboratory, we have 35 calibrations for forages, 30 calibrations for grains and meals and byproducts, and plus TMR and BMR calibration we have. So it means that the global networks have huge capacity to overlap all of the forages and feeds what we use on a farm, on a dairy farm. And it's important for the users, because they don't want to share the samples and send to different laboratories the different samples. And there are many parameters. That's why the global networks generally use packages, parameter packages tailored for the specific forage type. Look at the parameters. There are so many. It's sometimes confusing. And silage experts, in a case, they ask me why we need so many parameters. I try to explain why. So, these are the general parameters. These are the fiber packages. These are the easily degradable carbohydrates. These are the energy fermentation parameters and CNCPS data and different German, French, or Dutch evaluation data set. This large number, it's important in one report because there are different users and the different users need different parameters. What I would like to mention, what is important from this list, the American laboratories, CVIS, Rock River, and Dairy One follow the American standards. And they have satellite laboratories in Europe. They have a service, but they don't adapt to the local requirements. It is a limitation. But they have special data, what are necessary for NDS or EMTS softwares, and they can produce an XML, an uploadable XML. And it's an important point in competitiveness, because if the nutritionists don't have to type the data into the software, but they can upload an XML, an adequate XML, and the software will use this data automatically, it's a big advantage for the user. In the case of Eurofins Agro, the strategy is different. They adapt to the European circumstances, and they can provide German, French, and Dutch data because we have German, Dutch, and French softwares also. And these softwares need parameters also. And this is in Europe, it is an advantage of the Eurofins Agro. Okay, so why we need so many parameters? Because in one report, we can send messages to a crop manager, in the same time the mechanist, in the same time the farm manager, the veterinarians, and the nutritionist. For example, the crop manager needs digestibility data in order to decide the harvest time, or the protein, soluble protein, and nitrate concentration give information for him about fertilization efficiency. PNDF, CSPS, soil contamination, or dry matter can give information to the mechanist whether they have done, they have made a good job or not. The farm manager need nutrient content, energy content, and fermentation quality because they have to be sure that there is no acidosis risk or ketosis risk. And they have to check whether the bunker management was okay or not. And nutritionists need other data, for example, CNCPS data, degradation data, for the dynamic rumor model. That's why we have so many data on a report. Everybody can find what he needs. And we don't have to care what we don't need. But it's important to see that these are not useless data. Okay, so, portable NIR, it is the future. This portable NIR can be research-grade NIR systems, or plug-and-play systems, or industrial online NIR systems. They are not baby anymore, but they are not still adults. They are teenagers, I think. It means that they are not ready, but they are developing. So why I tell it? Because accuracy is a question. Wet material heterogeneity is a challenge. And the scientists and the companies are working very hard on it, and it's developing step by step. The research-grade system can maximize the analytical accuracy. The plug-and-play system are very handful, and we can use this equipment on farm. And we have online system, just like a Harvest Lab or the PolySpec, when we can use the NIR in the TMR, in the mixer wagon, or in the harvester. These are very good opportunity. The online system can increase the representativeness of the samples, so there are many advantages. But there are problems. The problem is heterogeneity of the vat material. The problem is the moisture content, which can make interference, and the environment and measurement circumstances. So it means that accuracy, precision, and reliability can be questionable if this kind of devices can't manage it, and it is under development. What kind of parameters they can measure? A lot wet chemical parameters can be measured by NIR, portable NIR, but not all of them. So it's not enough now. That's why I thought that they are teenagers, because they need to develop more. And digestibility data are the most critical. The accuracy is the most questionable. Okay, what kind of forages we can detect with portable NIR? There are many forages, but not all of them. And the farmers do not like to share the sample to send to another lab. That's why the portable NIR system needs further development, but they are in a good way, because it's getting better and better. Okay, so if we will be able to use in the future the portable wet NIR, is a very good pathway toward data-driven smart forage management and the real-time precision feeding. It is the future, not the present, but the future. Okay, and the far future. So within the next 10 years, the cloud-based calibration will help in standardization of the big database. The machines will learn to evaluate the big data sets. The artificial intelligence will help in prediction and advisory. And the real-time nutritional monitoring will give us opportunity for continuous measuring. Conclusion. So the NIR system has become indispensable, I think, in forage analysis. The global dry NIR networks accelerate innovation and improve accuracy. But in the future, the hybrid calibration system would be the solution. Calibration quality determines reliability, and ongoing development of calibration databases and predictive methods is essential. And biological parameters, including digestibility, is still more complex than TMR and PMR. That's why we need further developments in accuracy. We would need a worldwide harmonization of the reference chemical and in vitro methods to increase comparability of the near and the wet laboratory results. And the portable wet NIR is the future, and it helps us continuous monitoring and the continuous and much better forage management and precision feeding. So it was a horizontal view. You find the details in the paper, and don't hesitate to send email to me if you would like to know more about the global NIR networks. Thank you for your attention.
Dear Sylvia, thank you for your lecture. Yes, I have a small question for you, because you spoke about the local calibration, yes, and our farmers have the harvester with Harvest Lab.
Yeah.
And there is typical for the global calibration, because they calibrated according DLG in the Germany only, yes, and they used the results whole Europe, yes. And what do you mean about the results?
It is a company and their own data set, so it's not, I don't want to criticize their efforts, but I think need more time to develop the calibration data set. It's hard work because they measured NDF and starch and dry matter in a flow. So it's not easy. It's a heterogeneous material and it is in time measurement. At the moment, I say that it's worth to check the results in a wet lab or a dry near lab, because sometimes there are sometimes we don't understand the data, and when we made a comparison, we have found differences. Of course, this is the future, and if they develop the data set, accuracy and reliability will be better and better.
Thank you. And you spoke about local calibration, and I have to ask you, which size is local calibration?
So in my mind, a calibration based on 1,500 sample. One calibration, one nutrient, one sample, one type of sample, and for one parameter. So for me, it's very hard to imagine how can a local laboratory may have this kind of capacity. But the local laboratories will develop step by step with the time, because if you have more time, you have more samples, and accuracy will be better and better. So this is the biggest disadvantage of a local laboratory, the sample number. But there are many advantages, because they can investigate the local samples. So it means that the heterogeneity of the samples is much smaller.
Thank you. And another question, please.
Reinhard Resch, Silvia, thank you very much. My question is, what do you think about the role of ring testing of wet chemistry labs on international way to evaluate the values of the reference regarding standardization and getting better references for this global databases?
Of course, when we, in my country, when we check the NIR results and compare with wet lab, we choose a laboratory with international certification. It means that that kind of laboratories take part in ring test and international and national ring test, and it helps. But there are different problems. Different countries use different methods. So it means that the chemists of the different countries, at least in Europe, should discuss what kind of method would be the best, for example, for sugar. And because in one wet lab use ESC, ethyl extraction, and other labs use water-soluble carbohydrate. And in the ring test is okay, because they confirm the method, and the ring test confirm that, okay, this result is accurate according to your method. But the ring test will not tell that, please use another method, because it's more updated or more frequented or more company use, so more laboratory use. That is my problem, that wet labs can be very accurate and the ring test will not help in harmonization of the methods. AOEC standards are okay and it helps a lot, but because there are continuous development, sometimes the AOEC can't follow the steps so quickly as they would need. I don't know the solution. I see the problem. I can't tell you what would be the best way, but some kind of harmonization would be necessary. Or the knowledge that if I compare a wet lab and an NIR, not always the NIR has the wrong result, because the different result doesn't mean that one is good and one is wrong. It's different. But farm manager can't do it. We are the scientists. We should motivate the scientific team to help to start harmonization. If scientists knows more about this problem, maybe we could step further to solve this problem. But it's huge work.
Thank you.
Thank you.
Thank you very much. And now we have first coffee breaks, yes, and we will meet again here at 11:40, yes. And after this coffee break will be Reinhard Resch, please.
set off for a Venetian fountain, an ancient temple. They sailed all the way to the Orient in a little boat. A romantic minaret rose up like a lighthouse, guiding their way. They climbed to the minaret's highest gallery and they took a day trip around a landscape adorned by neat roads. With the wind in their hair. At the chateau, they climbed into a carriage and set off for a Venetian fountain and ancient temples. They sailed all the way to the Orient in a little boat. A romantic minaret rose up like a lighthouse, guiding their way. They climbed to the minaret's highest gallery and looked out to see the tip of St. Stephen's Cathedral. A Viennese waltz rang out. Make your holiday truly romantic. Visit the Lednice complex, the Czech Republic, land of stories. Sped to their destination with the wind in their hair. At the chateau, they climbed into a carriage and set off for a Venetian fountain and ancient temples. They sailed all the way to the Orient in a little boat. A romantic minaret rose up like a lighthouse, guiding their way. They climbed to the minaret's highest gallery and looked out to see the tip of St. Stephen's Cathedral. A Viennese waltz rang out. Make your holiday truly romantic. Visit the Lednice complex, the Czech Republic, land of stories.
Is he this one?
Resh.
Resh?
Right.
Is this Resh?
This man, Resh. From Gumpenstein.
Okay. May we start again? So it's my honor to be here with my dear friend, Mr. Jambor. I will be then leading this section for the rest of this morning. It's again a great opportunity to hear some of our fellows, and then we will start by Dr. Resh Stockmiller. Sorry about my very poor Germany. So he will speak on behalf of the applied lactic acid bacteria on fermentation quality of grass silages from the Austrian dairy farms. So please take your time.
Thank you very much, Luis. It's a great pleasure for me, and I thank Václav, my neighbor and friend, for this talk in the next section. Let's start. A few introduction words to you. In principle, ensiling of forage has a lot of practical challenges to preserve nutrients qualitatively and quantitatively for a longer period. Butyric acid of first cut grass silage in Austria is above 12 gram per kilogram dry matter. So it's one of our main challenges. We have too less nitrate in our permanent grassland, and Clostridia level therefore is high. According to Mr. Palo, he was a great scientist in Germany, he said lowering of the pH as quickly as possible is one of the key factors of controlling enterobacteria and Clostridia. So it's a goal for us to get quick milky acid fermentation. And in this topic, application of homofermentative lactic acid bacteria like Plantarum improves the fermentation process. It's one thing we have in importance, and the second, heterofermentative species like Buchneri increases aerobic stability. It's the second goal for sugar-rich grass silage. So I want to show you an evaluation of LAB treatment on different grass silage qualities of a project we are in monitoring every 4 years in Austria, and also one exact trial on wet grass silage to show you the effort of LAB treatment. Grass silage in Austria, you see our map, and we are now here in Lednice. It's an area with a high amount of arable land. We in Austria have disadvantaged areas in the mountains and with high grassland content, more than 90%. So of our total used land, we have 50% permanent grassland, and 50% of this is conserved as grass silage. So grass silage is of importance in our country. And our first challenge, I said it to you before, for grass silage in Austria is butyric acid and failures in silage quality. So we have recommendations. Dry matter content for clamp silos for 30 to 40%, and also butyric acid with less contents of only 3 grams. It's very low recommendation. Hard to get it for us. We see only 18%. It's not a successful story, I have to tell you. In this overlapping area, have success in these recommendations. Now, I want to show you the treatments in Austria with different applicants. Yeah? The relative stable situation until 2020 was 80% are non-treated of the grass silages. Yeah? We have 50% LAB treatments, 3% chemical, and 2% other products. And in our project 2024, wow, we have a bit of change. 2/3 of the whole grass silage in Austria was non-treated, and we have 46% of clamp silage, clamp silage with treatment, and 41 or more LAB treatment on different silage systems. A few words to material and methods. In our monitoring, we checked out 600 samples of Austrian dairy farmers, and we trained the person who sampled all this material. We have analysis in a standard way. My colleague Gerald Stögmüller is here, and he do the whole work. Thank you, Gerald, for that. We can present the results in a few minutes. Yeah? So, data of silage management was evaluated in a questionnaire. We have different metadata of all the silages collected to have a good analysis for quality and management together. I want to show you a few words to silage trial S78 with a new product of homofermentative LAB on wet grass silage with 24% dry matter. We want to show the advantages of LAB treatment. And we use statistical analysis. I want to show you in the table. And this is the table with the results. LAB, homo, hetero, and a mix of them against no additive with the abbreviation CON. Yeah? And you see in the results there are improvement of silage quality. Yeah? Especially lowering of butyric acid by LAB homo and LAB mix, also lowering pH by all LAB treatments. So the goal of Mr. Parlow is really good. Yeah? We have also seen improvement of silage stability, aerobic stability, because acetic acid was developed by LAB heterofermentative bacteria. We indicated by analysis of 1,2-propandiol, and I show you a XY plot in the next slides. A bit of non-success maybe in average. This was the story of treatment of chemicals. We don't see a a good access or success in butyric acid. So, first of all, you know this slide I told you before? Now, this is the story of LAB HOMO. 69% is in this area of recommendations, not only 18%. So, next, LAB hetero, 57%. And you see the average curve is a bit higher. LAB mix of homo and hetero, 60%, is similar to that of LAB hetero. So, in general, we can see chemical additives, it's nearly the same as the non-treated varieties. LAB HOMO, I think that's important for recommendations. What dry matter content is favorable for LAB HOMO? 25 to 35%. LAB mix, 35 to 45, and hetero, 40 to 55. Also a part of the border to haylage. Yeah? In this slide, I want to show you the improvement of acetic acid in Austria. So you see our target area is more than 10 grams of acetic acid per kilogram dry matter. And with LAB HOMO, oh, you don't get that. Yeah? There is much more production of lactic acid and not acetic acid. So you can't get high stable grass silage with that treatment. But with LAB hetero, there is a success. But you see the cloud of the points, it's very large spreading of the acetic acid contents. So a part of the treatments is very successful in acetic acid, but not all. So this is the mixture, a bit better in acetic acid than the con variants and the chemical additives. I want to show you this slide because there is a good relationship, a correlation between acetic acid and 1,2-propandiol, and you can use 1,2-propandiol very good for indicating the success of Buchneri. So R squared of 88%. And against that LAB HOMO you have nearly only a few 1,2-propandiol dose or content in grass silage. Now, this is a result of the exact trial, showing you the dry matter loss if you use no additive or LAB HOMO at a dry matter content of 24%. And it's interesting that the reduction of dry matter loss is very spectacular with 6.8% after 19 days and 9.4% after 190 days. Yeah? If we made an economic example to evaluate the advantage of treatment of LAB HOMO of 1,000 cubic meters of silage, it's equivalent to a yield of nearly 60 hectares of the first cut. So we see 3.9 hectares you produce more loss. If you have the whole mass, you harvest it, you lose the yield of 3.9 hectares in dry matter. And you must have a supplementation of that. Yeah? And I think this slide is very important to show you that energy or nitrogen losses are not lower, they are higher. You have more loss in quality in such a field of wet grass silage. Yeah. Advantage. I calculated it and see 100 cows could be fed, in this example, 117 days more in comparison to the non-additive treatment. Yeah? So, conclusions. LAB improved the fermentation of grass silage quality. We have a faster pH reduction via LAB treatment. The best reduction of butyric acid formation was with LAB Homo. Reduction of mass and quality losses also via LAB Homo and LAB Mix. So we could have a good experience on that in dry matter contents of 24 to 35%. But be careful because of Homo treated silages, they are not as stable as you expect. Yeah? LAB hetero improved the aerobic stability because of the increase of acetic acid via LAB hetero, Buchnerei. Yeah? The goal for LAB hetero, 35 to 55%, especially high sugar grasses and too low feed-out ratio. So my conclusions for LAB treatment of grass silage at dairy farms in Austria, the benefits are feasible. Yeah, if conditions for LAB are good and best practice have to be done. If the LAB treatment works, the success in silage and livestock production is most likely. So I think that's a positive out-view to our experiences in Austria with LAB treatment. And I'm ready for questions, and thank you for your attention.
Thank you, very nice presentation. I have a question here. Seems to me that the LAB, I mean the LB, not LAB, was best fitted for the wilt, the higher dry matter silages. Is there any basic information why should be this?
In the higher dry matter values,
yeah,
we observed a relative good success in this drier conditions, but you have problems if you pass 60%. That's been the border, the edge where the fermentation support of applied lactic acid bacteria works very well. You cannot be sure that it works. Sometimes it can be good, but on the other hand, you have conditions that are not easy to control.
Thank you. Any other question? There, please.
Tomáš Sherry, firma Biofarm. I got one a really small question. Follow your results after fermentation and the level of water-soluble sugars after fermentation. Can you explain us which kind of chemical additives did you use?
The chemical additives are in a different configuration. We have all possible ingredients, yeah? Like hexamethyl and tetramine for example, you know, the Cofossil product, or acids like propionic acid, for example. So we have the whole family of chemical additives.
Yeah, but it's not answer on my question. Which kind of chemicals did you use in your trial?
In the trial, we don't have chemical additives.
But you showed that you used chemical additives.
Here we have no chemical additives. Here? Yeah. This was not the study of an exact trial. This was the monitoring of ELCA project 2024, where we have 600 of grass silage samples.
Well, we have time for a last question.
Congratulations on the presentation. My question is actually about that slide. So I'm a little bit surprised that only 31% of the farms or the samples that you analyzed used inoculants. Would you say that that's representative from Austria, or is it representative for that region or that specific type of silage? If you're talking maybe about corn silage, would see bigger numbers.
So it's quite a part of the whole dairy farmers of Austria, and we cannot say in a secure way that this represents all of our farmers in total truth. Yeah? We do this monitoring since 23, yeah, and over more than 20 years, we got a picture and also a development of things we observe. So it's in our experience to put these informations, these analyses, these results in the cascade of years and learn of the different results we see every 4 years. Yeah? And this helps us to improve our understanding, our education in learning the farmers, what are the problems, what are solutions, and could give recommendations and develop recommendations. It helps us with such a monitoring project to fit us all together in silage making and improve silage quality.
Okay. Thank you again for your very nice presentation. Another round of applause, please. Our next speaker is Dr. Ivan Eisner, representing the German team. He will talk about the VOC, the volatile organic compounds on grass, silages, and whole plant maize silage. Please, Ivan, take your time.
Thank you very much. Thank you for invitation and the chance to present this study. Just in the beginning, for clarification, you see here the name Novonesis. So we are sponsor of this conference, and you see the sponsors are Christian Hansen, but Christian Hansen was in the past. Now it is Novonesis. So. Okay, the topic of my presentation is the effect of different combinations of lactic acid bacteria on alcoholic esters concentrations in grass and wool plant mice silage. And first of all, why we did this, study? So, very often from the field we hear if, for example, corn silage has high ethanol content, that the cows don't like this silage, the cows don't eat this silage. Yeah? And studies demonstrated already a strong positive correlation between ethanol concentration and ethyl esters levels in silages, especially ethyl lactate and ethyl acetate. And not ethanol, but these esters are discussed as having negative effect on silage palatability and intake. Yeah, but it is still discussed because some trial shows if you put pure ethyl lactate or ethyl acetate to the silage, that sometimes we don't see any negative effect of that. So they're discussed. The problem is that analysis of the alcoholic esters is labor intensive and is costly. And an equation based on ethanol content was proposed 2017 to estimate the sum of ethyl lactate and ethyl acetate in silages. And some laboratories use already this equation and put it this equation. So this is the equation. And some laboratories put already the results of the calculation already here. For example, this is a short screen from the lab analysis from a German lab. And here you can see already ethyl lactate and ethyl acetate calculated, and they put also reference value, and sometimes, the farmers, if they can get this analysis, they will think, oh my God, if I open this silage, my cows will not eat this silage. Yeah? But this is example from the corn silage from the farm milking 50,000 liters per cow per year without any problems on health or feed intake. Yeah? So, yes, high ethanol content is usually associated with high yeast activity due to poor silage management and delayed sealing. Yes, but for example, it was also reported that this regression between ethanol content and ethyl esters has different slopes according to the silage management on different farms. And for example, if pH in the silage is above 4.25, then we don't have any correlation anymore. And for a lot of grass silages, not from Austria, but for example from other countries, a little bit wilted, a little bit drier, they have automatically higher pH level. Yeah. So, but the labs still, for example, this lab still putting this calculation in the lab analysis even for grass silages. Yeah? And we know also that, for example, if you use Lactobacillus buchneri, they also produce a little bit ethanol. Yeah, because ethanol and acetic acid, because ethanol is a byproduct of acetic acid production by buchneri, and acetic acid inhibits yeast in this case. Yeah? And therefore, the objective of the study was to quantify alcohol esters in grass and maize silage, and then to see the relationship to ethanol concentration in these silages. We did 2 trials. One trial was done in grass silage, and we used round bale silage. So we prepared grass in round bales, and the storage period was 100 days before sampling. The bales were stored outside, and we used 3 treatments. One treatment was combination of homofermentative lactic acid bacteria, Plantarum lactis and Lactococcus lactis. Another treatment was combination of Lactococcus lactis and Lactobacillus buchneri. The third combination was the mixture of Lactobacillus buchneri, Lactobacillus zelivorans, and Lactobacillus plantarum. So we used the application rate, what is targeted for this product on the label. So, and in all cases, the target was to apply more than 250,000 CFU per gram. But after the harvest, we realized, okay, we applied the double amount. So it means the final concentration was double than expected, but it was, the target of the trial was not, it was a little bit different, so it was not that important. Main point, we applied inoculant, and we did few repetitions per treatment, so it was not designed that we have different number of bales, because the trial was designed for another purpose, but this is how many bales we analyzed later. Another trial was done with corn silage. It was pure lab trial silage. We did mini silos. We stored the mini silos for 109 days at room temperature. And in this case, we had corn silage without any additive, corn silage with mixture of Lactococcus lactis and Lactobacillus buchneri. The silage treated with mixture of buchneri, delivorans, and rhamnosus, and the silage treated with mixture of buchneri and plantarum. So here we measured already exactly the count what we applied, and the count was again above the target, but for the final experiment it is not a problem. And we did 5 repetitions per treatment. So, statistical analysis, we used JLM model with the treatment as a fixed effect, and for some parameters distributed, we use non-parametric approach for the significant analysis. The results, if you look for the fermentation, nothing special, so we can say as expected. Homofermentative mixture produced the most of lactic acid, the least level of acetic acid, no propionic acid, low level of ethanol, low level of propandiol. Mixtures containing heterofermentative lactic acid bacteria produced less lactic acid, but more acetic acid. Interesting is, for example, that we see here delivorans should convert propandiol to propionic acid, but in our case, we see the lower level of propandiol compared to another product, and we have a little bit increased propionic acid, but the main end product was propanol here. If you look for the maize silage, also nothing special. So we have higher acetic acid level in product using buchneri. Only this treatment, also with buchneri, would expect a little bit higher acetic acid, but in this case it was not the case. So, okay, alcoholic esters. To show better the alcoholic esters, I also put again the acids here, and we can see, for example, if we have higher level of lactic acid, automatically it was increased in ethyl lactate. If we have higher level, so in grass silage, and it was the same in corn silage. If we have higher level of acetic acid, we have increased level of ethyl acetate in grass silage and also partly in maize silage. And if we have higher level of propanol, then we have higher level of propyl acetate that is also alcoholic ester. So, the first conclusions, homofermentative strains produce more lactic acid and we have higher ethyl lactate. Lactobacillus buchneri produces more acetic acid and we have increased ethyl acetate. Lactobacillus delivorans increase propanol and increase propyl acetate. The question is now, what is about the calculated value of sum of ethyl lactate and ethyl acetate and they really analyzed. Here we can see what we see in the grass silage. So these crosses are the real value analyzed of some ethyl lactate and ethyl acetate, and these dots above, this is what was calculated by this equation. So we see that we see some correlation, but this correlation is not that strong, like, for example, not that high as predicted value. If you look for corn silages, again, the same situation. This is the calculated value according to the equation, and this is what we really analyzed. And if you look here, then, yeah, practically no real correlation to ethanol. So here we can put both together, and we can see that in most cases, yeah, the predicted value was higher than really analyzed. So the conclusion is silage inoculants may affect the content of alcoholic esters in the silage. but the predicted concentration of the sum of ethyl lactate and ethyl acetate were higher than the chemically analyzed values in all samples. And here we cannot say this could be effect on the lab, because it was the same lab analyzed ethyl lactate and ethyl acetate, and the same lab which was showing this equation before. Yeah, everything in the same lab. And in both experiments, the yeast and malt counts were below the detection level. It means the silages were good. So, and for the future interpretation, I would say under optimal enzyme conditions with minimal A exposure and silage inoculation with heterofermentative lactic acid bacteria, which reduce yeast counts, ethanol concentration alone cannot reliably predict ethyl lactate and ethyl acetate levels. And in situations where silage quality or palatability is of concern, then direct chemical determination of alcoholic esters is recommended to ensure accurate evaluation. So, thank you.
Ivan, thank you for your very nice presentation. This is very well fitted to the new trend of analyzing VOCs in silage, and the future will certainly consider the amount of VOCs on the dry matter and animal performance based on that. I have a very quick question to you. I noticed the conversion from 1,2-propanediol to propionic acid or either to propanol was not constant if you compared grass silages and corn silages. They were not pretty much the same trend. Is there any reason for that?
I would expect this. I was also surprised. Yeah, so I would expect like this. I don't know. I cannot explain it. We need more trials for that. Yeah, to see if it is really the case that in grass silage, I can say we did several tests, and all the time we see this conversion from propanediol to propanol. In corn silages, it was just one test. I cannot say this is the case. Yeah.
Okay, thank you. Okay, we have a room for questions now. Please, Douglas. Go ahead.
Yes, I just want to check from you. When I look at the data here, it seems that those inoculants didn't work well for maize silage production, because when I look at the lactic acid production, it was quite low than when you ensile maize without any additive. But when you look from the grass silage part, it seems it worked better compared to the maize. What could be the problem for that?
Yeah, the question is, so I cannot say it was not well. So what do you mean? Too low lactic acid concentration in the corn silage? You mean they didn't work well because the lactic acid concentration was too low? Yeah?
Yeah, in terms of the maize silage part. When you look at the grass
yeah.
part, it's much more.
But this is typical. In grass silage, usually we have higher level of lactic acid than in corn silages, because in grass silages, the buffering capacity of the crop is higher, and more acids should be produced to stop the fermentation. In corn silage, buffering capacity is lower, less lactic acid is needed to reduce pH. So pH we have in the previous one. So if you look for pH, in all cases it was below 4. In corn silage, it's fine. So, and we used heterofermentative lactic acid bacteria, or as a part of these combinations, and they convert lactic acid to acetic acid and a little bit ethanol. So this was normal fermentation pathway, so the results are not surprising.
Okay. One more question? Okay. Thank you, Ivan.
Yeah.
Is not our next speaker is Zilk. Is he around or she? This one here. Corn? Oh, okay, it's coming. Thank you. Please take your time.
Okay. Und hier geht's weiter. Ja, okay. Hello, my name is Judith Zielke, and I'm working for the company Dr. Pieper in Germany. Today I want to talk to you about the changes in lactic and acetic acid, pH, dry matter, and temperature during aerobic deterioration of oat whole plant silage. Oat silage is, in comparison to other grain whole plant silages, not very common, but oat is, in terms of nutrition and soils, relatively undemanding, and so oat can be, especially in regions with light soils, a good alternative to produce energy-rich fodder. Most grain whole plant silages have in common that they have a high sugar content in combination with a low buffering capacity, so that the fermentability coefficient is mostly in the range of 60. But the same parameters which make them easy to ensile let them also deteriorate easily after exposure to air. So aerobic stability is generally a critical problem of these silages. Lactate assimilating yeasts are commonly reported to initiate aerobic spoilage, as the spoilage generally starts with the oxidation of residual sugars and fermentation acids. On the fresh forage, you have mainly non-acid tolerant yeasts which die within the first 2 days after ensiling, so they have only a low impact on silage quality and no impact on aerobic stability of the silage. In comparison to that, you have the lactate assimilating yeasts, which are highly acid tolerant and can survive the whole ensiling process. The acid tolerant yeast can be divided into groups. Both groups have an impact on silage quality and on aerobic stability, but they affect these parameters in different extents. On one side, you have the family of the Saccharomycetaceae, which, for example, Saccharomyces cerevisiae. These are Crab-positive yeasts. They have a high fermentation potential under anaerobic conditions, where they convert sugars into ethanol and carbon dioxide, which leads to higher dry matter losses, as well as a high concentration of ethanol in the silage. However, these yeasts have only a low respiratory efficiency under aerobic conditions. On the other side, you have the family of the Pichiaceae, for example, Pichia crudiaf civis. These yeasts are Crab negative. They have a low fermentation potential under anaerobic conditions, but their respiratory efficiency is very high. So the Saccharomycetaceae mainly affect silage quality, and the Pichiaceae mainly affect the aerobic stability of the silage. The amount of yeast, especially of the Pichiaceae, can increase during the storage period due to insufficient compaction of the silage or air entrance when the silo is not covered correctly. But and this also leads to a lower aerobic stability. But in this trial, we added the yeasts before ensiling because we wanted to see which impact has initial amount of yeast on the forage, on aerobic stability, as well as on changes of different parameters during the aerobic storage. To improve aerobic stability, it is necessary to avoid a massive increase of these yeasts once the silo is opened. And in practice, you have two main strategies to inhibit them. One is the use of preservatives like potassium sorbate or benzoate, which can inhibit yeast successfully as soon as the pH is low, and they often combined with homofermentative lactic acid bacteria, which ensure rapid decline in pH in combination with anaerobic conditions, inhibit most of the undesired microorganisms in a very first stage of the ensiling period. So if you combine these, you can produce high quality silages which also have a high aerobic stability. But the chemical preservatives are relatively expensive, and they must be applied separately from the lactic acid bacteria, which make the application system a bit more complicated. The most common way to inhibit yeast in silage is the use of heterofermentative lactic acid bacteria like Lactobacillus plantarum. They are mostly from natural source, they are cheap and easy to apply, but these bacteria convert sugars to lactic acid and acetic acid, but the production of acetic acid also leads to slower decrease of pH and also to higher dry matter losses because carbon dioxide is built. To see the effect of acetic acid independent from the metabolism of heterofermentative lactic acid bacteria, in this trial we used homofermentative bacteria in combination with the addition of acetic acid. So we used our silage additive Bioseal, which consists of two different strains of the homofermentative lactic acid bacteria, Lactobacillus plantarum, and this bacteria were directly applied at the shopper. Then among the control groups, we made groups with 1% acetic acid in the dry matter and 2% acetic acid in the dry matter, and these groups we divided into subgroups, and to one of each subgroups we added yeast of the species Pichia crudiafcevi with an inoculation density of 1 million yeasts per gram fresh matter. The epiphytic amount of lactate assimilating yeasts was 10,000 yeasts per gram fresh matter, so we added the 100-fold amount. We ensiled in 1.5 liter glass jars and opened 3 jars of each variant after 3, 10, 49 and 90 days. So in all groups, the acetic acid further increased after 10 days of ensiling, but the acetic acid amount generally doesn't doesn't differ between the groups with or without yeast treatment. The dry matter generally remains stable within the first 49 days of ensiling. However, in all variants with no acetic acid treatments and 1% acetic acid treatment, the dry matter content decreased significantly after 90 days of ensiling. To determine the changes during aerobic storage of the silages, we opened the silos and homogenized the silage material and made of each jar 8 equal samples. In those plastic caps, which were slightly closed with aluminium foil, so that air has entrance to the silage material. Then we, of each jar, we took one of these samples and analyzed pH, lactic acid, acetic acid, and dry matter content. After 10, 49 and 90 days of fermentation, we also measured temperature to determine the aerobic stability according to Honig, and aerobic instability was reached when the temperature of the silage was 3 Kelvin above the ambient temperature. The aerobic stability increased with increased amount of acetic acid. In the variants with 2% acetic acid, all silages remained stable for more than 7 days. However, there were no directed impact on the yeast treatment of the silage material. Then we measured, as I said, acetic acid, lactic acid, pH, temperature, and dry matter during the first 7 days after opening the silos. In the upper row, you see the variants without yeast treatment, and in the bottom row, you see the variants with yeast treatment. And here, for example, with no acetic acid treatment, you can see that here the red line marks the point when aerobic instability due to Honig is reached. And in the same range, all other parameters changed significantly. So when the temperature rises, you also have a significantly increase of pH and significantly Thank you. And a significantly decrease of dry matter, acetic acid, and lactic acid. In comparison to that, on the right side, we have the variants with 2% acetic acid. There you can see when the temperature remains stable, you have no changes or no decreases in all other parameters. The same results we can see after 49 days of fermentations. Also here we have an increase of temperature, and the same point an increase of pH and a decrease of lactic acid and acetic acid. And in the variants with 2% acetic acid, we had no changes in all these parameters. So conclusions. First, the treatment with yeasts have only a low impact on the ensiling process, as well as acetic acid treatment, which might be due to the low fermentation potential of the yeast. The aerobic stability enhances with increasing amount of acetic acid in silage, but the initial amount of PCSC has no effect on aerobic stability. Temperature, acetic acid, lactic acid, pH, and dry matter depend highly during aerobic deterioration. So each of these parameters shows amount of aerobic instability. And also we had no temporary differences between lactic acid and acetic acid. So no of these acids is preferentially metabolized by the yeasts. Thank you.
Thank you very much for your very nice presentation. I will start addressing a question to you. I noticed in one of your first slides the highest level of acetic acid added to the silage. It dropped the dry matter content, if I'm not wrong. Is this the dry matter?
No. Yeah.
It's quite constant, this effect. When you added the highest level of acetic acid, the dry matter content is supposed to be decreased. In your very last dark green bar is the highest,
Yeah, it also decreases, but the decrease in dry matter was not significant. And as you can see, it's also the decrease in dry matter is also lower in comparison to the other groups.
Okay. Is this dry matter corrected by the volatile compound?
It's only corrected by lactic acid and acetic acid because this was the only volatile compound we measured.
Okay.
So there's no, we didn't know the concentration of ethanol or other.
Yeah, maybe if you apply the equation for correcting dry matter, this depress on dry matter content might be adjusted. This is my suggestion.
Yeah. Okay.
Okay, next questions, please.
Thank you for your presentation. Did you count the number of lactate assimilating yeasts at each opening day? I asked the question because did
yes,
they
we measured that
at each opening day.
But I don't have a slide of this here,
okay.
But I can tell you that so the epiphytic amount of yeast was 1 million,
yes.
And the yeast per gram fresh matter, but the amount of acetic lactate assimilating yeast was only 10,000 per gram fresh matter. And during the first 3 days of ensiling, both amounts were equal. So the rest died, as I explained. And in the further duration of storage, the amount of lactate assimilating yeast decreases.
Okay, thank you.
Another question over there, the other corner.
Thank you for your presentation. I have a question. Why you chose 10 days and 40 days fermentation periods, not 15 days, maybe 14 days.
Because we made this trial according to DLG.
It's written in DLG guidelines, yes?
3 days is if you want to determine the silage quality, if I'm not wrong. Aerobic deterioration you measure after 49 days.
But what reason, for example, 10 days fermentation length? It's to catch fermentation speed or other things. How you can explain? Why I'm asking? I am explaining because I don't know. We're doing too, but sometimes I have questions, and maybe you answer me about that.
I think his questions is trying to make a point on the time of measuring the aerobic stability. Why have you decided about this?
The measuring points.
Yeah.
Because the 10 days we did because we want to see how fast the silo can be opened under these conditions. And 49 days, is a common point of DLG regulations.
Okay, I think you can talk each other during the lunchtime. Okay. Any other question? Thank you very much. So now we are moving to our last very presentation in this morning, and this will be led by the Chinese group. So Wei leading this group, and Wang, effects of Artemisia RG, active matter on the aerobic stability of whole crop corn silage.
Good afternoon, everyone. I'm Huili Pang from Zhengzhou University, from China. It's my great honor to share our team's research effects of Artemisia RG active matter on the aerobic stability of whole crop silage. Now I will share with these 3 parts. As we all know, whole plant corn silage is very important in the ruminants industry because it with good palatability, high digestibility, rich nutrition, excellent storage stability, and inservability. It can balance season variation in forage supply. But because it is full of nutrition, so when it after the insealing, when it open to feeding animals, it may cause aerobic spoilage. When oxygen exposure, the stability will lost, and the pH will rise, and the proliferation of aerobic microorganisms and may produce mycotoxin. And this mycotoxin feeds, if this silage feeding the animals, maybe cause the animal the immune suppress and affecting animal husbandry. If these sick animals feed the, these sick animals, maybe the toxin residues to the milk and the meat, and these residues may also transfer to the human and affecting the human health. Currently, the measures to control the aerobic stability maybe include these three measures. Physical measures usually regulate the moisture content and the chop length, but this is low lab efficiency and increased the costs. Chemical drugs will inhibit aerobic microbial growth, but it may have some pollution to the environment and the animal health. The biological measures also with addition of enzymes and some microorganisms, but the better strain is very difficult to select, and the stability is very difficult to ensure. Artemisium algae is a very famous herb, both can as food and as the medicine. It exhibits multiple biological functions, including antibacterial and anti-inflammatory activities. And feeding with Artemisia algae can promote animal growth and enhance immune function in our before research. So in this research, we want to compare the fermentation quantity, chemical composition, and the microbial community of whole crop corn among different treatment groups to review the effects of Artemisia algae activity substances on silage quality. And we want to know if this new, if these additives, if it can provide some new insights for the development of novel feed additives. This is a material, some three bioactive nutrients from Artemisia algae, include essential oil, crude flavonoids, and incorporeal. And also, LAB strain, Lactobacillus buccineri was used as a positive control. This is the design of the experiment. There include 6 groups. Black control only whole crop corn, and whole crop corn with incorporeal and with oil and with crude flavored, and also with these three mix. The sixth group is with LB. The method, the scale is 300 grams each in the lab, and the ensealing time is 90 days. After 90 days fermentation, it Arabic to the Arabic exposure time is 1, 3, 5, and 7 days. After the open, each was measured fermentation quality, chemical composition, and microbial community. This table shows the fermentation quality, chemical composition, and microbial counts of the fresh sample, include the crop corn and the AA. As we can see, both these two samples contain high levels of water-soluble carbohydrates, including that both have favorable initial fermentation characteristics. This is a dynamic change in fermentation quality of the whole plant corn during Arabic exposure after 90 days of ensealing. As shown in the table, at 90 days ensealing, group M means 3 additives mix exhibited the lowest pH along with the highest contents of WSC. And LA, while group LB had a significantly higher acetic acid content than the other group. And as Arabic exposure time increased, group A had significantly lower pH than the other groups, while group M had a higher WSC content. This may indicate that adding AA active substances helps maintain the corn silage quality. This table shows the dynamic changes in chemical composition of whole plant corn during Arabic exposure after the ensealing. The NDF and ADF contents decreased across different treatment groups, which may be attributed to the fiber degradation, and the CP content declined, but there were no significant difference among the treatment groups, which may be due to the inhibitory effects of a low pH environment on proteolytic microbial organisms. And this may be indicates that in sealing of the WPC silage with the addition of AA active substances can facilitate the breakdown of complex carbohydrates and release more nutrients. This figure is a bacterial community analysis of the silage at the phylum and genus levels. On the phylum level, the dominant bacteria phylum in the WSCC fresh samples was proteobacteria, whereas after the 90 days ensealing and during the Arabic exposure, the dominant phylum was Firmicutes, and we all know LAB is in this genus, in this phylum. On the genus level, after 90 days ensealing, the dominant genus in the CK, A, and M groups was Lactobacillus, and during Arabic exposure time, Lactobacillus remained the dominant genus in the A and M groups, while in the G, after 3 days exposure, this group also shifted to Lactobacillus Plantibacillus as a dominant genus. This fig is a fungal community analysis of the silage. For the fungal phylum levels, the dominant fungal phylum in all treatment group was Ascomycota. But in the genus level, the dominant fungal genus in fresh materials was Alternaria. After 90 days in sealing, the dominant fungal genus in group H and M was Candida. During Arabic exposure, the relative abundance of Candida increased in all treatment groups. For the conclusion, after 90 days in sealing, group M means 3 mixture addition group had the significantly lower pH than the other groups, along with the highest contents of lactic acid and WSC content. And the group M had the highest contents of DM and CP and the lowest contents of NDF and ADF. During the Arabic exposure, the dominant phylum in the group supplemented with AA active substances were Formicus and Ascomycota, and the dominant genus were Lactobacillus and Candida. In a conclusion, the addition of AA active substances improve the fermentation quality of the whole plant corn silage and reduce the nutrient loss and enhance the feeding value of the silage. Thank you very much for the listening. Oh, thank you, Luis.
Thank you for your very good presentation. I have a question. I understand the most important focus of your research was on the flavonoid concentration and essential oils coming from Artemisia, right? Have you ever considered to measure the microbial counts from the Artemisia?
Yes.
You did?
Yes, we also did.
Okay, is there any special numbers coming from this?
Maybe in the fresh material, the microbial number is not so different as other grass, other forage grass.
Okay, thank you.
Thank you.
Any other question, please? We have a room for more questions. In your opinion, the combination of the internal compounds of Artemisia is more important than isolated by themselves? I mean, flavonoids plus essential oils and other molecules that might be there. This interaction in between those molecules is the main dominant effect? Or
yes.
is more for flavonoids or more for essential oils?
Yes, yes. For the because in our before research, we also use the whole crop AA, and also use this active substances. We found that it's the effect is from the active substances.
Okay. Thank you.
Thank you very much.
Any other? Okay. Thank you very much again.
Thank you again.
So this is time for new guidelines from Sonia. Thank you for your attention for this morning.
Yes, I have some organization instruction for you. Now there is a lunch. Everybody has a tag about the lunch. There is a date, so choose the right one. The lunch is here in the dining room, and go straight from the main door. I think that Hanna Sinkova or people on receptions show you the way. And after lunch, there will be a there will be a photo, all of participants here. So I think it will be 10 minutes to 2 o'clock. Yeah. So be there, please, to show how many we are. So enjoy your meal. Hello? Can you hear me in China?
Yeah.
Okay, show us your pictures. Yeah, we can see you.
Nice reporter.
So I think that it's time to start the afternoon section.
Okay. Good afternoon, ladies and gentlemen. We keep going our program. Our first guest is a fellow from China. He will speak about on the effects of Artemisia RG addition on the fermentation quality and greenhouse gas emissions of corn stover silage. You can keep going. It's your time. And welcome.
Okay. Respected professor and teacher, it is a great honor to share my research finding with you today. The title of my presentation is Effects of Adding Artemisia archaea leaves on Fermentation Quality and the Greenhouse Gas Emissions of Corn Star Silage. This study aims to explore a novel green additive for silage to improve the utilization efficiency of crop store and reduce environmental pollution. Next, I will present my report in several sections. First of all, I will introduce the research background. Corn straw is a very common crop by-product in China. It is rich in water-soluble carbohydrates, crude fiber, crude protein, and other nutrients, and has high feeding value. However, fresh corn straw has bloatability, low nutritional value, and low digestibility. When directly fed to livestock and poultry, which greatly limits its practical application. Silage technology can effectively solve these problems. The main procedures of silage include harvesting, complication, and fermentation, compared with direct feeding. Silage can significantly improve feed palatability, nutritional value, and digestibility. At present, it has been widely applied in animal husbandry. However, traditional corn straw silage still face two major challenges. First, during the installing process, undesirable microorganisms such as miscellaneous bacteria, yeasts, and enterobacters multiply rapidly, causing quality deterioration of silage and posing possible risk to feed safety. Second, this gas producing half microorganisms generate large amounts of greenhouse gas like carbon dioxide and methane during fermentation, which not only lead to nutrient loss in materials, but also exacerbate environmental pollution. To address the above issues, we are looking for a novel, safe, and efficient silage additive. In this research, we selected Artemisa argi. It has excellent biological function. It can inhibit harmful bacteria, reduce mycotoxin production, and promote the growth of probiotics. At present, common silage additivity are divided into physical, chemical, and biological types. We hope that Artemisa argi can become a new type of additive different from the traditional three types. If this additive works well, it can not only optimize the quality of TMR, but also cut down greenhouse gas emissions from silage. This is of greater significance for the sustainable development of animal husbandry and the realization of carbon nutrient goals. Now, let's look at our research paper. We mixed Artemisa argi with corn straw to make a total mix silage ration. We evaluated 4 aspects: microbial community, fermentation quality, chemical composition, and greenhouse gas emissions. Our aims are developing wormwood silage additive, optimizing store silage, and supporting carbon nutrient in livestock farming. Next is our experimental design, divided into 3 parts: materials, treatments, and detection indicators. First, materials. We use the second harvest town in Bei'ai, wormwood, and Zhengda 958 corn store. Then for treatment groups, pure corn store, 30% wormwood, 60% wormwood, and pure wormwood as the control. All silage were fermented for 6 days, followed by 3 and 7 days of aerobic exposure. We tested the quality of fermentation, nutrients, greenhouse gas emissions, and the microbial community. Now let's move to the analytical methods part of our experiment. Next, let's focus on fermentation quality, shown in Table 1. This table displayed dynamic change of pH, water-soluble carbohydrates, and lactic acid across 3 treatments during the whole ethylene parent treatment and ethylene days both significantly affected or indicator. Notably, the 60% AA group reached the lowest pH of 4.31 and the highest LA content of 39.50 at day 30, indicating super fermentation performance. Next, we move on to chemical composition. As shown in Table 2, when we saw the dry matter, neutral detergent fiber, acid detergent fiber, and crude protein cross all groups. AA rest grow protein and cut fiber contents. At 16% AA, we got the lowest NDF of 256.23. The lowest ADF of 164.23, and the highest CP of 119.98. Overall, 16% AA showed the best improvement in cornerstone strategy nutrition. Now, look at figure 1. The dynamic curves of pH and LA graph way show that 30% and 16% AA groups keep much lower pH throughout the whole fermentation period, while the pure cornerstone soil control had a slid pH rise. For LA in graph B, the 2 AA treatments always maintained the higher LA levels than CS, which proves wormwood effectively promote LA fermentation. Playing and analysis of cornerstone silage across different fermentation duration revealed that the groups supplemented with 30% and 16% AA, meeting the consistently lower pH values and higher CP contents throughout ethylene, while reducing ammonia, nitrogen, and NDF and ADF concentrations, thereby optimizing overall silage quality. Analysis on the dynamic variation of greenhouse gas emissions, figure 2, indicated that the 13% and 16% AA groups inhibited a pronounced inhibitory effect on the production of carbon dioxide and methane. Now, we move to the microbiome community result in figure 3. Graph 3 shows Purium level composition 1D3. Dominant bicarbonate threads from protected bacteria. The harmful bacteria to beneficial phagocytosis. As seen in Graph 3b, by this study, the 60% AA group had the highest relative abundance of firmicutes, mean wormwood, effectively erase favorable microbe during silage fermentation. By regulating Peter, including amino acid, biosynthesis, and discarboxylic acid, metabolism. It ultimately suppresses the production of greenhouse gases. Carbon dioxide and mist. (16% AA was added to corn store silage. Reduced greenhouse gas emissions. Lower pH and cooled fiber content. Improve LA fermentation efficiency. Increase slope carbohydrates. Thank you. Thank you.
Thank you, Dr. Wang. A very nice presentation. I have a question to you. Are you hearing me properly?
Okay.
Dr. Wang is presenting on behalf of the Zhengzhou University, led by Professor Yimin Chai. Congratulations, very nice contribution. Your data is very impressive. The amount of gases that was mitigated by using Artemisia was really interesting. You have a changing on the microbiome, mainly because you have more Vicella strains. And then the metabolomics was also driven towards the changing on the gas production. So my question to you is 30 and 60% represents on fresh basis or dry matter basis?
Dry matter.
Are you following me?
Hello? Dry matter.
Maybe there's a delay. Oh, fresh basis. So this is a large amount of Artemisia, right? How do you mix this? This is a lab trial, but do we have some larger scale trial mixing so large amount of Artemisia? This is a kind of a practical question. Or not yet? Not yet? Not in a commercial, not in a commercial basis yet. This is a basic trial, right? Okay.
With me.
Okay.
He just started now, so not work so long time, and also his English not so good. Maybe don't understand your question. I'm sorry. We are sorry about that.
No, no problem at all. We can pretty much follow you, and maybe you can help on the answering the questions. More questions, please. This is a very interesting and innovative trial. We have a question there.
Could you clarify what is the dry matter content of the cone stover itself? If you have only cone stover, what is the dry matter content?
Dry matter. Yes.
Dry matter.
Dry matter, yes, dry matter basis.
No, I mean the dry matter concentration of cone stover alone. What is it?
Sorry,
Cone.
I don't hear.
Sorry, you mean the cone stover?
Yes.
The moisture is low.
Yes, how low?
多少?
Percentage.
Maybe I think about 60%, just after harvest. So not so drying, can fermentation. Yes, that is a cone stover. We use the cone stover. So it's very low moisture. Okay. Sorry.
Sorry.
Any other question?
Yes, it can. We directly inserted the fresh corn straw without a sun-dried in our channel.
Okay. Any other? Professor Emin, I have a curiosity. Is this corn stover harvested in a late maturity stage? Okay. So it's a corn stover after you harvest the grain, right? Okay. Well, it might be a little bit different if you are using the corn stover in a middle age, like in a whole corn plant stage for whole plant silage. Yeah. All right. So we have to move forward. Again, a round of applause for the presentation from China. Our next speaker will be...
Okay, thank you.
Jatkauskas as a leader of the presentation. And he will speak about the effects of Lactobacillus plantarum and Pediococcus pentosaceus inoculants on the fermentation characteristics and aerobic stability of grass legume silages. Take your time.
Thank you. Oh.
It's, for me, sometimes in practice, very difficult to talk after lunch. Please do not sleep. I will try to be short. First of all, I would like to thank organizers for possibility to be here, and I am proud to present our short work. Why it's work happen? It's mostly practical work for us, because very often our farmers asking regarding what inoculant or biological additive, but from one company, from another company, because we have a lot of dealers in our small country. And I'm thinking, what about bigger country, how much they have? Now you can see his background information, like others information regarding the silage additive using, of course, and to demonstrate efficiency is it's objective for this product, what we use it as additive for increasing silage quality and feeding value. Test material is very simple. A fast cut mixture of perennial ryegrass, red clover, and timothy was harvested, wilted, up to dry matter concentration 30%, chopped, and sealed in 3 liters glass jars. And the tested additive was just La Classique, produced by German company Acera. Laboratory silage. As I tell before, it is chopped and prepared was being a suspension or solution of inoculant and sprayed. It's not very long work to produce a mini silage. It's a very small quantity, but one time we tested single strains, one time 19, another time 23. And in this time we need to produce, because the replications or repetitions needed at least 5 from one treatment, it was being produced at 400 mini silos. And in what I can say, when who are doing these trials, you need to look all possibilities for chemical analysis, what you need to organize some laboratories and to use this hard work to produce silage. Because silage, mini silage produce is very important, how you produce, and it depends results. And why we're doing, if question will be, because different people's feeling mini silo, yes? And that it will be right in same compaction density, we are no dry matter content, weighing for each people, employer who are putting inside, and he need to put all what's been weighed and to achieve density, what we are needed. It's some statistical, you maybe read already. We are using experimental setup, it's traditional. For example, grass, legume foraging this time can be maize, can be other things, can be byproducts. First of all, you know, we need to test, to analyze raw material from what we're producing. We are very often doing testing pH value after 2 days for maize. it needs to be 3 days. I'm sorry, it's mistake. For grasses. To speed fermentation look very simply. And pH value. And after that, analysis after 90-day fermentation. But what we had question can be done high stress. And it necessary to decide. I think it's better to use this widely this of German this for testing silage additives. It's a very good thing. And can be fermentation periods. But finally, our purpose was one final results. And aerobic stability test. We are additionally doing fresh weight loss because very important. Of course, aerobic stability is temperature changes during aerobic aeration, aerobic exposure, and pH value, lactic acid, yeast at both counts for hygienic purposes. Results shortly, what you can see, you can see materials, what was produced from Perel Vegras and Clava Timothy. Its chemical composition, buffer capacity, and microbiological characteristics presented too. And shortly, fermentation results, you can see graphs, acids, total acids, acetic acid, changes, butyric acid. I don't know, you can see, and maybe I need to tell you that better, higher, you can see in his figures, I think. Alcohol concentration, ammonia concentration, acidity value, pH after, and this included pH after aerobic stability test. It's very important. You can see with inoculant, aerobic stability, pH value, it's not different from this value of silage when we open the silage and sample it. This analysis was being done by Gary Wickett from chromatography. And silage's dry matter recovery is very important. We get much better dry matter content, and dry matter was lowest significantly, and dry matter recovery was being higher for inoculated silages. Sometimes what is economical question, not me, but to explain for farmer, for example, how you spend for inoculant, and from 1 ton, we can, when using inoculant, we can get about 100 kilo of grain. It's better to maybe for some understood. There's sometimes megajoules of metabolized energy is sometimes difficult to explain from people. And aerobic stability results. You can see this equipment recording every 6 hours. After that, just before aeration period. Before aeration period, this one. Like it. And after exposure to air, you can see results. And conclusion. Under controlled condition, we got that our used inoculant improved fermentation quality of grass legume silage, reduced dry matter, nutrient losses, and inhibited yeast and mold growth, and increased aerobic stability. It's very important aerobic stability, and I think is important role. It's to inhibit yeast growth, because yeast is general enemy for this aerobic deterioration, for silage, to keep silage in good conditions. Thank you.
Thank you, Professor Žetkauskas. It's a great opportunity to demonstrate some data from the Lithuania. So I have a question. Your results are very good. Overall, the overall results, they are demonstrating the effectiveness of the combination of both strains compared with the control.
Yes.
When I look to your data, I noticed you were recommending the counts of 6 times 10 to the 5 CFU per gram. This is in a general basis, this is a little bit higher than the commercial basis. Is this a recommendation?
This recommendation we don't change. As I talked before, we tested, and what this company recommended to farmers, we tested this recommendation. And I know it's very high quantity of bacteria per gram of colony-forming units per gram of forage. It's high. It's I don't know why, they don't explain, but it's very high. For example, mostly we did in our scientist life very many trials with residocolants, and it was been from 1,000 to 1,000, mostly 150,000, and this is the biggest, was it 600,000 per gram, per colony-forming units per gram of forage.
Okay, thank you. Other questions, please? We have a question from that side.
It's just an observation. After 90 days, in the control, the amount of lactic acid was lower and the ammonia was higher, but yet the pH of the control was lower than the inoculated.
Yes, because lactic acid, as you know, is a mostly aggressive acid, lactic acid, and the pH value is dropped very quickly. If we achieve lactic acid very quickly, high quantity, pH value or acidity stay lower very quickly. It's very important. Why we using inoculants? To achieve speed of fermentation. It's not chemical additive where we restricted fermentation. It is regulation of fermentation.
It's just after 90 days, I would have expected if lactic acid was lower and ammonia was higher, the pH would be
How
higher
to explain
as well.
for you? 90 days, maybe it's different. Some doing 120 days, but theoretically and classical silage makers was written. It's needed mostly 5 weeks for full fermentation. After that, you know, it's stable period stay. That's 90 or 120 days, I think it's not different, but some selecting 120 days, some 90 days, maybe 70 days. We have had some trials in short fermentation period after 60 days, what happened.
Thank you. Another question? Any other? So thank you very much.
Thank you. Thank you.
So our next speaker is Dr. Milimonka. She will speak on behalf of the efficacy of a preservative containing propionic acid, sodium benzoate, and sodium propionate for controlling molds in different moist grains. So take your time and welcome.
Thank you very much. Good afternoon, everybody. I hope that after you had a good lunch and my presentation will be not so boring, you know. And my presentation will be short, simple, and more from practical side and from technical side than scientific. And I will represent today the trial we have done in our company. And these trials we have done together with my colleague, Dr. Andreas Milimonka, but now he is in well-deserved retirement. So it's my pleasure to be here. And my topic today will be the preservation of moist grains, and of course in aerobic condition. And as you can see here, the presentation title is Efficacy Study of Preservative 1A700. This number is regarding Europe regulatory, and this additive says that in composition we have sodium propionate, sodium benzoate, and propionic acid. And we have tested with this trial different grains, and we wanted to test the dosage, to find the right dosage, and to check during the different storage period how many molds, how many CFU we will get. So, yes, how we can avoid it. Molds and yeast and different kind of bacteria. Of course, first of all, is very important well cleaning of the grains, and then quickly preservation when we get the grains from the field. And of course, we can use a different kind of preservation. We can use drying, we can use the preservation with chemical silage additives in anaerobic and aerobic conditions. Here, as I mentioned, we choose the preservation in aerobic condition. And yes, I already, I think, mentioned all these methods we can use. And of course, the target is to reduce the contamination of bacteria, molds, and yeast. And as you know, propionic acid is worldwide used. Of course, there are a lot of scientific research about propionic acid, but when we are talking about the preservation of the moist grains, it is very important that with propionic acid we have some huge disadvantages. It is harmful for our skin, so it's not safe to use, and also it's not so safe for agricultural machines, because you know the corrosiveness is we get higher, and so we thought that we need some product to create some product with buffered salts, and later I will show the formulation. And we have checked this formulation in our trial. Yes, and as I mentioned, that preservation of high moisture grain is essential to prevent spoilage, maintain nutritional value, and reduce mycotoxin contamination, ensuring feed quality and safety. And of course, also another very important topic is that with preservation of moist grains, we can reduce the costs of drying and the costs for fuel. You know that now the cost for, in general, for drying grains going higher, and the cost for fuel is also very high. Of course, also with preservation, we can reduce the dry losses, field losses of delayed harvesting. And also, you know that the moist grains are very has high nutritional value for dairies, beef, and we can also end the fattening of the pigs with moist grain. Yes, I already mentioned these things, that propionic acid has huge disadvantages regarding harmful for skin and the safety of usage. Propionic acid in general, as you know, is very good to reduce the molds and yeast. And sodium propionate and sodium benzoate, we can also have some antifungal effect, and we can broaden this activity. And we have produced the product of these 3 different ingredients. So the objective of trial was to evaluate the mold control of the non-corrosive preservative A1700, which is based on propionic acid, sodium benzoate, and sodium propionate, and we have tested in wheat, barley, and maize. The location was in Germany, in Bitterfeld, and the trial starts in July 2023, and we finished the trial in March 2025. So, as I mentioned, you can see the concentration of different ingredients in this product A1700. And you know that with these ingredients, we can achieve better results and better effectiveness. So, materials and methods. The grains we used were taken from commercial farm. So we used, I would say, normal cleaned grains. And also, for example, for wheat and barley, we done also the remoisture because the dry matter content was too high, and we needed to add more moisture. So we remoisture with water and leave the grains for 30 minutes to get this moisture. You know that for growing of molds, the percent of moisture from 18 to 22 is the right one. And for maize, we just leave for trial the natural moisture we got, and for maize was 30%. So yes, for each grain species, we used 5 kg, and it was treated respectively with these amounts of products. We wanted to achieve 4.5 and 9 liters per ton. And yeah. So the practical points of this trial: the grains were placed into a food processor, and the feed additive was just using a hand sprayer continuously during the mixing. The grain material was stored in 1.5 liter jars containing holes in the bottom and the cover. So we achieved the aerobic condition. We have slightly closed these holes with cotton pads, but still the oxygen and the CO2 had the possibility to go in and go outside. So the grains had the possibility to breathe, and also the grains of the different moisture levels were stored in different climate chambers at 25 Celsius. Also 25 Celsius is the right temperature when you have the moisture of grains from 18 to 22 or even higher. So you can expect really great growing of molds and at this temperature and at this moisture level. So the storage I mentioned before was aerobic conditions, and from the delivered grains, and the grains after the storage time of 6, 12, and 24 months, we took subsamples for analyzing the mold counts, and it was done using plate on the agar. So we tested the results after 6, 12, and 24 months. And I think, okay, also the data I will show in the tables will be the data set of 6 replicates. Yes, and the results. In wet wheat grain. You can see here, I highlighted this in yellow color. It's very difficult to show, here. So you can see here that with higher dosage, and we have achieved better results. And also you can see that after 6, 12, and also 24 months, we had the significantly differences between the control and between the silage additive. So, what I wanted also to say that, for example, after the 6th month, I would recommend to use 4.5 liters because to use the 9 liters, it doesn't make sense. You can see here there was no significant differences, and looking from the economical side also would be, after the 6 months would be better to use 4.5, and then later you can see that after the 12 and 24 months, I would recommend to use 9 liters. Yes, barley grain, we got a little bit differences here from results. You can see that after the 6 months, we got the really dosage depending results. You can see that after the 6 month with 4.5 liter, we achieved the right results. And after there with 9 liters also. And I would say that during the time period, you can see that also after the 24 months, you can have with this combination really great results. I didn't mention that you can see also that in the control from the start, the counts of yeast, of CFU, very quickly achieved more than 1 million in the control. So the wet corn, the corn grain had, of course, the more higher moisture, and they were 31 and 29. And we also tested here the counts. And you can see that after the 6th month, we reached with 12 liters, the great results, significant differences. And after 12 months, we reach also significant differences with usage of 12 or 15 liters. So Of course, we can see here that this preservative works very well, and but when we are talking, of course, well cleaning first is very important first, and then we can think about the usage of this chemical silage additive. Yes, and conclusion, we really got great results, and the trial also confirmed that this formulation works, and this formulation is safe for your skin because the pH of this formulation is around about 5, so also it is less, it is more friendly for agricultural machines. So you can see here photos I took from farm. They are growing pigs and piglets, and of course these grains also they're stored under aerobic conditions. So in the picture you can see I am holding maize grains, and these maize grains is after 24 months, but still the quality, I didn't find that I could see some, you know, visible molds on the grains. So we are happy that the trial confirmed our previous trials, and yes, thank you very much for your attention.
Thank you, Dr. Petkut, for your very nice presentation.
Thank you.
I have a question. It's more a curiosity. Is the intention behind of this trial just to store the whole grains, but not producing a grain silage, right?
Yeah, it was, here the idea was to check in aerobic conditions and to find the right dosage, and to look how it works on different grains. But of course, for example, this formulation works also very well for silage, for ensiling in anaerobic conditions. So not only this formulation, it is not only for the aerobic storage.
Yeah,
Yes.
The idea behind of my question is the targeting of 22 to 18% moisture. This would be very restrictive for a grain silage. In grain silages, usually we add more water in order to have a deeper fermentation. And then the addition of these chemicals, they might be more effective if you do have a better condition for decaying the fermentation. But that's why I asked you before if the idea was only to preserve the grain, whole grain, instead of producing the silage by itself.
Yeah, the idea was to keep them, to storage them, and as you know, for example, the farmers wants to dry the grains and to have the moisture content round about 14 or less. So we chose this moisture content from 18 to 22 because from the practical conditions, it's the right one to check the molds. Of course, we can also have the more higher moisture, but we checked because, you know, if we, for example, had more moisture, for example, for wheat or barley grain, then you could expect more the germination, but not the mold, grow of molds. So the idea was to check the contamination of the molds, but not to get the growing, you know, of the seed. So.
Okay, thank you. Please, other questions? We have many behind there.
Thank you very much for this presentation. I just have a question regarding the use of the grain after using the preservative? Can you use it only in animal nutrition, or is it also possible to use it for human nutrition, for beer or bread making?
Have I understand good the question you are asking, or it is can we use this for
if you can only use it to feed animals, or
Yes.
if you can also use it to make bread or beer, for example, from grains that you preserve like that?
No, this formulation is not, how to say, registered to use for bread. It's registered to use for different kind of animal, for feed of animal, yeah.
Thank you for your presentation, very nice data. I have just two aspects, technical and economical.
Okay.
Technically, to apply 9 or even 15 tons, 15 liter per ton, so seems to be really high. Yeah, I don't know if it's possible technical in a big scale. And another question is, what is return on investment? Is it not cheaper? Just dry the corn to the dry matter content of 12 and it's all?
You know, with now the higher cost for drying now, what we have in nowadays, so it will be more cheaper to use this formulation than to do the drying. But also, for example, from the practical side, I showed the photos from the pig farm. They are using 10 liters, but what they are expecting, you know, also that they have a higher nutritional value, and they have really well weight gain of the pigs. So not only, you know that the moist grains have a very high nutritional value and better digestibility, higher palatability, and so on. So, of course, the production maybe can be, at the end, you know, it depends on the farm, how they can keep their economical situation. But for example, from this farm, so they are really well in the production and they are happy with this formulation.
One more question here.
Congratulations for the presentation. My question is actually on those lines about the nutritive value and the health of the animals. Have you guys analyzed the nutritional value of those grains and any sort of mycotoxin test was performed?
Of course, for this trial, no, we don't analyze. But before, we have done also a lot of trials regarding nutritional value and mycotoxin contamination. So yes, you of course can reduce the mycotoxins first, and you can have at the end the higher nutritional value with chemical preservative. No.
Any other? Okay, thank you very much.
Thank you very much once again.
So our next presentation, again, is a remote presentation, and another very good contribution from Zhengzhou University, led by Professor Yiming Chai. So this time we will hear about Dr. Yan. Are they there? Dr. Yan?
Hello, is there someone? Perfect, we can see presentation.
Ready?
Okay.
Dr. Yan, are we following us?
Okay.
Okay. Today we will have the presentation regarding the effect of a plasma-activated water treatment on the fermentation quality of wheat straw silage. Please take your time. You can start.
Okay. Good afternoon, everyone. I'm Yan Yang from Zhengzhou University. Today, I'm glad to share our research with you. The topic is how plasma-activated water improves wheat straw silage. Straw silage is a common farm waste. Making straw into good feed is very important for farming. In this talk, I will talk about our work in 3 parts: research background, experiment, and main results. First, let's look at the background. Every year, we produce more than 700 million tons of straw. If we turn straw into animal feed, we can save lots of feed resource and help farming develop in a green way. Now we use silage to keep straw fresh. Silage works in this way. We keep straw in a tight place. Good bacteria turn sugar in straw into lactic acid. This acid lowers the pH value and stops the feed from going bad. It can keep nutrition for a long time. But we still have problems. Bag fungi and moths often grow during silage making. They break down nitrogen and make harmful taxes. These taxes are bad for farm animals, so we need a better way to stop harmful microbes. Here we use plasma-activated water, or PAW. This special water is made by using low temperature plasma on common water. It has special active substance. This substance can kill or stop the growth of bad bacteria and fungi. What's more, PAW is safe, clean, and low cost. For this reason, we did these studies, use PAW to treat wheat straw and check how it changes silage quality, nutrition, and microbes. This is the main part of our research. We did 2 kinds of tests. First is a lab anti-fungi test. We first found out the main fungi from silage. Then we grow these fungi in control dishes and PAW in them. The result is clear. PAW can greatly slow down the growth of fungi. It works well to stop harmful modes. Second is the wet straw silage test. We set 2 groups. Control groups, normal silage treatment. Test groups, treat straw with PAW before silage. We took samples on different days and tested many indexes. We tested pH value, lactic acid, acetic acid, and ammonia nitrogen. In the earlier stage, both groups' pH dropped quickly. The PAW group had a lower pH and much more lactic acid. More lactic acid means better silage. The PAW group also had less ammonia nitrogen. It tells us less protein was destroyed. Our results show that PAW helps silage start faster and become better. We also checked nutrition like raw matter, fiber, and crude protein. After PAW treatment, raw matter increased, so fewer nitrogen were lost. Hard fiber decreased, so the feed is easier for animal to eat and digest. Crude protein become higher, which makes the feed more nutritious. We studied bacteria and fungi in silage. Tests show PAW changed the types and numbers of microbes. It cut down bad fungi and bacteria, and helped good bacteria growth. The whole microbe environment become more standard for silage. Now let's sum up our conclusions. First, PAW clearly improves silage quality in the earlier periods. It makes more lactic acid and keeps the pH at good levels. Silage ferments faster and better. Second, PAW makes silage more nutritious. It keeps more protein and dry matter, and reduce hard fiber. The feed value of wheat straw is improved a lot. Third, the key reason is that PAW changes the microbe community. It controls harmful microbes and builds a good growing environment for useful bacteria. To conclude, plasma activated water is a good green and useful method for straw silage. It works well and is worth small research and wide use. That's all for my talking. Thank you for your listening. If you have any questions, please feel free to ask me. Thank you.
Thank you for your presentation. Thank you, Dr. Yan. Very nice presentation. I have a question to you. Are you hearing me?
Okay. 可以的。
The plasma-activated water was effective on changing the fungi population. However, it was not so effective on changing the bacterial population. At the same time, you have had some changes on fermentation. How do you explain that? You understand me?
Yes.
One of your conclusions is the bacteria population wasn't changed that much, but the fungi population was. But when you look to your fermentation, the fermentation was pretty much changed. So is there any good explanation for that?
Bacteria and fungus is all influence, and bacteria and fungi is our influence.
Okay, maybe you are implying that the fungi changes in the population might be responsible for some of the fermentation changes, right?
Yes.
Okay. Next question, please. Thank you for your answer.
Okay, thanks.
Other questions from the audience?
I think it should be a mistake in your table. If I look for the lactic acid concentration in the treated straw, on day 30 you have 151 gram per kilogram dry matter. I think it is 15.1. Otherwise, I cannot explain it, because how much sugar has to be in the straw to produce this high level of lactic acid? So. But anyway, even 40 gram of lactic acid in straw, it means we have a certain amount of sugar available for the fermentation. Have you analyzed the water-soluble sugar content before siling? Because we have dry matter, NDF, AGF, and crude protein. And the treatment 3 days, 30 days. Yeah, but it is after 3 days. Yeah. So, have you analyzed water-soluble carbohydrate content before enzyling on day 0? What was the level there?
Yes. Yes. Before. Yes. Before this experiment, I.
Maybe the link is not working properly. I believe there is a delay. Are you hearing us? I think she's not there anymore. Okay, a round of applause for them. Well, this was the last presentation of this afternoon. Now, Sonia, you have any announcements or no announcements?
The last presentation, was cancelled because a few days ago we have noticed that the visa wasn't granted from Pakistan. So I'm sorry that we cannot have any other opportunities, but luckily we are out of time right now.
Yes. So we shall move for the poster section now?
Yeah, we will move to poster section.
Okay. Thank you for your attention. Now we are moving for the poster section. Thank you.
PM, 6 p.m. I'm sorry, I usually forgot what is PM and what is AM. But here in the audience, there will be refreshment for you, and who want to stay out, there is party tents and some tables and chairs for you. So welcome here, and I hope that it will be a fine after party.